functions and relations. In almost every physical phenomenon, we realize that one quantity always depends on another. For instance, your height depends on your age. The temperature depends on the date. The area of a circle is dependent on its radius. The cost of mailing a package depends on the weight of the package. So we use the term function to describe this dependence of one quantity on another. For example, we can say the height is a function of age, the temperature is a function of date, the area of a circle is a function of its radius, and so on and so forth. So in this section, we're gonna provide the mathematical definition of what we mean by a function. Let's start by this definition. A function, f, is a rule or a correspondence that assigns to each element x in a set A one and only one element called this thing in a set B. So a function is a correspondence, it's a rule between two sets, A and B. So you have a set A and you have another set B, and you have this correspondence between the two that's called F, which takes elements from here to elements here. So for example, it takes this element X and maps it to an element in B, and that element here is denoted by this image. Okay, so this symbol represents the element that F assigns to X, and you see the dependence. It's made up of F, which is the mapping, and the X, which is that guy. So it makes a dependence between that element and its assigned value or its assigned image. Okay, so this guy F parentheses X means it's the image of X under this mapping F. Okay. All right. So another thing is it assigns for each such an X and A in that set A, the departure set, one and only one. So it maps it uniquely to an element in B. Okay. So it has to map it. This is number one. And it doesn't map it to more than one element. For example, I cannot have this X going to another place other than this element. Okay, so let's take an example. How about this? So let's say I have a different element, let's call it Z, and this function F maps it to some other element. Let's call it sure, this guy is F parentheses Z as we used to have before, right? How about we give it a name? How about we give it the name T? Okay, and how about we give this guy the name Y? All right. So is this thing a function? Well, to be a function, it has to be a mapping from one set to another, which is the case, and it has to map uniquely its inputs, its elements in the set A. Well, is every element in the set A mapped somewhere in the set B? Yeah, X goes somewhere and Z goes somewhere. Now the uniqueness part. Is it mapped uniquely? Does X go to a unique place? Yeah, it goes to Y. And does Z go to a unique place? Yeah, it goes to this guy T. Correct? So this is a function then. Alright, So how about, let me just erase those guys. Let me just keep the y and the t. Okay, so let me just keep the y and the t. Let me take the other scenario. So this function here, this mapping, this rule is a function, right? We just discussed it. How about now I take the following situation. How about we let z go now to also y. So now x goes to y. So y, you can think of it as f parenthesis x, right, as we used to have. And z is mapped to y and to t. So y is f parentheses z and t is f parentheses z, if this is a function. Let's check if this is a function. Well, how about the existence of an image for every input? Does x go somewhere? Yeah, it does. And does z go somewhere? Yes, it does. So that part is okay. Now, the uniqueness part, the only one element part, does x go uniquely to an element in B? Yeah, it goes just to y. So far so good. Does z go uniquely to an element in B? Well, z goes to apparently two distinct elements in B. One time it goes to y, one time it goes to z. So the uniqueness part fails in this context. As such, this correspondence, this rule, is not a function, because it doesn't map, every element. It violates this part, the uniqueness part. There's one element in A that doesn't go uniquely to an element in B. Okay. All right. Another scenario. How about this? Let's take one more element. How about we take an element A here and we map it to T. All right. Now, is this a function? Think about it. Again, to be a function, every element here has to be mapped uniquely to an element in B. Does x go to a unique place in B? Yeah, it goes to y, which is a unique spot, a unique place to in B. Does z go uniquely to an element in B? Yeah, it goes only to t. So far so good. Does A go uniquely to an element in B? Does it go to one and only one place in B? Yeah, it goes just to T. Sure, T is shared by Z and A, but this is not the issue. This doesn't violate the definition. The definition is about every element in A is mapped to a unique place in B. It has a unique assignment in B. Well, X has a unique one. Z and A have each one of them has a unique image in B, a unique assignment. Correct? Even though one of them is shared, but that's not a problem. It doesn't violate this. It doesn't violate the definition of a function. So this is a function. Okay. All right. How about if I have an element B here that goes nowhere? So before I added the B, this is a function, right? Now if you add it, what happens? Does this remain a function? Well, to remain a function, I also need B to go uniquely to an element in B, capital B, the set B. Well, B goes nowhere. So as such, it violates this part. There is an element in capital A, in the set capital A, namely little b, that goes nowhere. So it doesn't have an assignment. And as such, it doesn't have an assignment, right? So as such, this is not a function, because there is an element in this set A that goes nowhere into B, that has no assignment. And for it to be a function, it has to assign each element in the set A to an element in the set B. So as it stands, this is not a function. Okay. All right. Now, how about if I have, let's say an element here, call it M. Okay. Now M is in B, but the M is not an assignment to any element in A. Does this remain a function? So remember, before we added the M, everything was good, right? This thing was a mapping, was a function. Now, if you add the M, but now in B, what do you think? Does this remain a function? Well, for this to be a function, I mean, that's the definition, it's right there. Every element in A should be mapped to one and only one element in B. Well, does X go to a unique place in B? Yes. Does Z go to a unique place in B? Yes. Does A go to a unique place in B? Yes. That's it. We don't mind elements in B not being seen by elements in A, right? So there may be elements in B which are not hit by elements in A, which are not assignments to elements in A. That's not a problem. It doesn't violate the definition. This is different than what we had before when we had the B here, right? So when we had the B, there was an element in A which wasn't assigned to an element in B, which clearly violates this definition. But as it stands now, M, which is an element in B, is not an assignment to any element of A. That's fine. Okay. B is thought of as the ambient space of where the assignments live. Okay? Which means there may be elements in B which are not seen by elements of A. Okay? Alright, so if I add, I mean, it doesn't matter how many ones I add more, that remains a function, as long as each one in A is assigned uniquely to an element in B. Okay? So let's keep going with the definition and provide a couple of terminologies. So the symbol, this guy, f parentheses x, you read it as f of x or f at x, and is referred to as the value of the function f at x or the image of x under f. Okay, so you can either, so you read it as f of x, and you can either call it the value of the function f at the point x or at the input x, or the image of the input x under the function f. Alright, so these guys are images of these guys. The y is the image of x, the t is the image of z under the function f, and also the t is the image of a under the function f. Alright. The set A in the discussion is called the domain of the function. So the domain of the function is the collection of all the accepted inputs through the function. Okay? If you think about the function as a machine, A is the collection of all the acceptable inputs through the function f, through the machine f. Okay? Alright. The range of the function f, is the set of all the possible values of f of x as you vary x throughout the domain A. Okay, so the range is the collection of all the possible outputs. For example, here the range of this function as displayed on the screen, is just y and t, right? It's the collection of those 2 points, y, t, because these are the only 2 outputs through the function f. M is not a possible output. So M is part of the ambient set B, right? Which is the ambient set where the range lives. Okay? So the range is simply y comma t in this case. Think about the function as like a flashlight in a dark room. Okay? So if f is a flashlight in a dark room, and if you turn the flashlight on, you're gonna see a piece of the room. Okay? You're gonna only see a piece of it. So B is the dark room, and once you turn the flashlight F on, you're gonna only see a piece of it, right? So in this case, you only see y and let's turn them green, so these are seen through the function, right? You only see this piece in this case. Make sense? So you only see this piece, this region. This is what the flashlight F allows you to see in this context, and B is the dark room. Okay? So that's what the range is. One more time. What's the range of a function? Is the collection of all the possible outputs, meaning if you vary the input throughout the domain of the function, in this case the set A, so if you vary the input here, for each input you're gonna have an output. So for each input you're gonna have an output. The collection of all the outputs is what we call the range of the function f. Okay, so mathematically, how would you write the range? It's the collection of images that look like f of something, and that thing lives in A. Okay, so mathematically, this is how you write it. You see it at the bottom of the screen. The range of the function f is, remember, curly brackets means set. It's the set of elements that look like f of something, right, where this thing lives in the domain A. Make sense? One more time. The range of the function f is the collection, so curly brackets, is the set consisting of how does each element in the range looks like? Well, we talked about it. Every element in the range looks like the image of some element of A, right? So it's the image, so f of something coming from A. So f of something, that thing lives in A. Okay? So collectively, if you collect all these guys as you vary the input in the domain, you collect outputs. The collection of all of these is what we call the range of the function. Okay, so don't think about x as being a particular element like x here. It's a generic element in the domain. You can call it x, you can call it star, you can call it bullet. It's just a placeholder for the input through the function f. Okay. All right. So to summarize this definition quickly. What's a function? A function is a mapping that maps every element in a set A, which we call domain, uniquely to an element in the set B. And the image of an element x is called f of x, right? The image of the element z is called f of z. The image of the element bullet is called f of that bullet, right? Okay. And f of x is called the value of the function at that point x, or the image of that x under the function. And lastly, the range is the collection of all the possible outputs when you vary the input throughout the domain. Okay? Alright, so let's take an example. Let's look at this example here. Let f be the function defined by this. So what does it mean? So you have a function, you have a rule, right? And they told you it's a function already. So they told you that it maps uniquely every element in its domain to a unique element in the target space. So if this is the domain A and the target space B, the function takes any input in A, let's call a generic one X, and maps it in a unique fashion to an element in B. That guy is f of x, right? That guy is f of x. But in this context, so f of x is the output or the image of x under the function f. But in this example, we have a concrete recipe for this output f of x, right? It's x squared plus 5. So instead of having f of x, an abstract representation of the output, I have a concrete one. I have x squared plus 5. So I'm gonna rewrite this as x squared plus 5. So what's x squared plus 5? It's the output through the function f for the input x. You see, x is an active ingredient in this recipe, right? So the output depends on the input, as it should, right? I mean, this is the notion of function. It's about dependency. Okay. All right, so this is how this function operates. The question in part 1 is as follows. Express in words how f acts on the input x to produce the output f of x. Okay. So how does the express in words? You gotta use pure words here to say how f operates on an input. Okay. So let's see. Let's zoom out. Okay, so let's write it here. Part 1. Just use any word. I mean, write the how f operates using your own words. You don't have to write it the way I write it. Just come up with a sentence representing the output. The way I'm gonna do it is, I'm gonna say that the function f what does it do? What does it do? Well, you take an input, you plug it in through the function, and this is how the function operates. Well, it squares the input, and then once it gets the result here, it adds 5 to it. Correct? One more time. You plug in x in this machine f. To produce the output, the function is going to do 2 steps. The first step is going to square the input, because x is the input, right? It's going to square the input, and then once it gets a result here, it adds 5 to it. Okay? All right, so the function f squares the input, and then it adds 5 to the result. Correct? This is how it operates. Make sense? All right. So that's part 1. Part 2. Evaluate f of 3, f of negative 3, and f of square root of 3. So what's f of 3 again? F of anything is the image of that thing through the function f, right? So this is what this symbol means. What's f of anything? Well, f of anything, if you're not comfortable with x, how about a bullet, right? F of anything, f of a bullet, is that bullet squared plus 5, right? Remember, it squares the input and then adds 5 to the result. And that's exactly the wording or if you want to verbalize this expression here. Okay, so back to this. Evaluate f of 3. So who's gonna take the role of the placeholder bullet in this context? It's 3, right? So I'm gonna plug in 3 here, and 3 is gonna propagate and sits here, right, in the recipe of the output. So it's gonna square the 3, and that's 5 to the result. Let's do it. So part 2. F of 3, again, I'm looking at the recipe, right? F of 3 is the square of that 3, because the bullet is 3, plus 5. So the square of my 3 plus 5. Correct? And what's the square of 3? 9 plus 5, which is 14. Okay? Make sense? Alright, f of minus 3. F of minus 3. So the input now is gonna be what? Whichever sits in between the parentheses is the input, right? And who's playing the role of the input here is minus 3. So I'm gonna plug in minus 3. The recipe of the output is gonna be the square of the minus 3 plus 5. So I'm gonna square the input, which is minus 3, and then I'm gonna add 5 to the result. Correct? Remember, if you don't put the parentheses, if you write this means the order of operation here is different than here. Let me make it clear. So this means you are squaring first, right? You are squaring first, which means you're getting a 9 here, and then you are taking the opposite. So the timing is different than this. This is different. You are taking the opposite first here, and then squaring the result. Make sense? So here this means minus 3 times itself, which is 9. This whole thing is 9, right? This whole thing here is 9. As opposed to here. I'm squaring 3, so that's 9. And then I'm taking the opposite of the result, so that's going to be negative 9. Okay? So they look very similar, but the timing is different. The timing is off here, right? It's scrambled a little bit. So here you take opposite followed by taking square. Here you take the square, and then you follow that operation by taking the opposite. Okay? All right. So let's go back to our context. Okay, so as we discussed, this is a 9 plus 5, same result, it's 14. Correct? This is okay. Remember, the output may be shared by multiple inputs. For example, here, the input 3 and the input negative 3 have the same output. The same output, that's fine. Remember, functions map uniquely every element to an element in the target space, right? So 3 is uniquely mapped to 14, and minus 3 is uniquely mapped to 14. So this doesn't violate that f being a function, correct? According to the definition. Okay, very good. We discussed this just earlier, right? Okay. Lastly, in part 2, f of square root of 3. F of square root of 3. Let's go down a little more. So f of square root of 3. Well, let's not forget how f operates. F of anything is the square of the thing plus 5. And who's my thing here? It's square root of 3. So I'm gonna square the square root of 3. So I'm gonna square the square root of 3. And then I'm gonna add 5 to the result. Yes? So we get this. And now what is the square of the square root of 3? The square of square root of 3. This is a 3, right? Okay. So this becomes 3 plus 5, which is 8. Alright? So f of 3 is 14, f of negative 3 is also 14, and f of square root of 3 is equal to 8. So the output through the function f for the input square root of 3 is simply 8. Excellent. Moving on, part 3. Find the domain and the range of the function f. Remember what the domain means? Domain means the collection of all the possible inputs, right? So on the picture, I mean, what is the set A? The domain. So what's accepted through the function f? Well, if you just investigate the situation here, what does f do again? It squares the input and then adds 5 to the result. Well, if you plug in any number, can't you square any real number? Can't you square any real number? Yes, I can square any real number. Remember, squaring means multiplying this thing by itself. I can multiply a number by itself, right? Or with itself. This happens for all x, so no constraints on x in this case. I can plug in any number. So you can square that x, and then, which can be done for any real number, and then once you get the result of this guy, the square of that input, you can always add 5 to any number, right? So the two steps again are, you're squaring the input, you can square any real number, and then because you can square it, so this is gonna be some number, whatever this number is, I can always add 5 to a number. So it looks like the process is very smooth, no matter what x is, as long as x is a real number, right? Obviously the understanding here is x is a real number. So there are no constraints on x for the output to be produced, right? As such, the domain of this function, so the domain of f is all real numbers. Remember again, domain means the set of all the possible inputs through the function f, all the acceptable inputs through the function f. And this function f here accepts anything because it squares the input, and I can square any real number. Once that thing here, this thing, is produced, I can add 5 to it, right? This happens for any real number, and once this exists, you add 5 to it. So it looks like no constraints on the input x, and because of this, I'm gonna accept all real numbers as inputs, and hence the domain is the set of all real numbers, which means boldface R. Correct? Very good. Hypothetically, let's take the following situation. Suppose that instead of having this as an output, suppose the output is simply 1 over x, right? Suppose the input is 1 over x. Clearly here, if you plug in 0, the output is gonna be 1 over 0, and 1 over 0 is nonsensical, right? 1 over 0 doesn't exist. I don't know how to divide by 0. So as such, I have to place a demand on x so that it cannot be 0 for the input to be produced. Okay, so x cannot be 0 for the expression 1 over x to be meaningful. Okay. All right, so in this context, the function is very nice. It produces this type of outputs. Okay. Finally, in this problem, I want to talk about range, or I want to talk about the range of the function. What is the range of any function? Recall, the range of any function is the collection of all the possible outputs through the function when you vary the input in the domain of the function. Correct? So that's what the range was. Okay, so look, look, whatever you plug in here, you're squaring it and then adding 5 to the result. Well, this part over here, which is a piece of the output, is at least 0, right? This can be any number which is 0 or more. If you plug in 0, you get 0. If x is 0, you get 0 for this guy, x squared. And this reaches any non-negative number, right? To get, like, if you want to reach 6, just plug in square root of 6, because the square root of 6 is 6. So my point is, this expression x squared reaches all numbers that are 0 or more, correct? And if you add 5 to this result, if you add 5 to this result, if this guy reaches anything that's 0 or more and you add 5 to it, this whole thing is gonna be what? 5 or more, right? Why? Because this expression x squared reaches any number from 0 onward. If you add 5, which means you are shifting the lower bound by 5, and that lower bound is 0, now shifted by 5, it becomes 0 plus 5, which is 5. And so it's going to reach any number that's at 5 or more. Okay? So as such, the range of this given function here is from 5 onward. That makes sense? So let me write the explanation here. So this is about the domain. Now for the range of f is 5 to infinity, right? Because, let's explain. Because the square of the input, okay, let's keep the input x. The square of the input is 0 or more for all x in R, right? For all x in the domain. So the square of x is gonna be 0 or more, and it reaches any number from 0 or more, right? So, and it actually reaches, so this expression x squared, it reaches any number bigger than or equal to 0, correct? So this can be 0 or more. Not only it is 0 or more, it actually reaches any number that's 0 or more. Okay, it doesn't miss anybody. That's my point. Okay, so because this and the fact that x squared plus 5 becomes bigger than or equal to 5 for all x in R, right? So if x squared is at least 0, as we discussed above, x squared plus 5 is at least 5, and also it reaches any number that's 5 or more. Okay, I'm gonna write the whole thing. So, and it reaches any number, so it's not missing anyone, right? Because it used not to miss any number from 0 or more, that expression x squared. Now x squared plus 5, you're gonna shift the whole thing. It's not gonna miss any number from 5 or more, right? Does it make sense? Okay, so if you would like to just illustrate this discussion just quickly here, if you know that x squared is living here, let's say, right? X squared lives somewhere here from 0 onward, right? It reaches 0, so 0 is reachable. Now if you add 5 to x squared, so you're shifting the whole thing by 5, so it's gonna start right there all the way to infinity, right? You're shifting by this amount, 5. Okay, that's what I'm saying. So this is where the number x squared plus 5 is gonna live. Make sense? Okay. Back to this little diagram here that we have. Let me erase these guys. So to be very specific, what's A again? A was all of R, right? The set all of R, the set of all real numbers. And B, the ambient space. Remember, B is not the range, it's the ambient space, correct? B is all of R, but the function f doesn't see all of R, it just sees a piece of it. It just sees a piece of it, right? A piece of it. And that piece, which is the range, is only 5 to infinity, right? Correct? It just sees a piece of it. Remember, this B, this ambient space, is where the range lives. But the range of the function may not be the whole thing, like in the case of flashlight, which is also the case here. So it's going to be a subset. The range is going to be a subset. It turns out that the range here is actually a strict subset, and it's not more than 5 to infinity. Okay? All right. Very good. All right. So now let's go to the textbook, section 1.3. Let's go to, let's say 23 here. I'm gonna do it orally. So I'm doing number 23. The question is, determine if the relation defines y as a function of x. So y is here as the output, and x is the input. So x lives here, so x can only be -8, and the y, it has 3 values, 3, 4, 5, and 6. So the question is, does this correspondence, or is this correspondence a function? Meaning, does it map uniquely every element in the domain to an element in the target space? By the way, the target space is also called codomain of the function. Okay, so this is also called codomain of the function. Anyway, so what do you think here? -8 is sent to 3. It's also sent to 4. It's also sent to 5. It's sent to 6. So since it's mapped to more than one element in the codomain, this is not a function, right? It violates the definition of a function. Remember, for it to be a function, every element in the domain should be sent to a unique element in the codomain. And this violates that, right? Okay. Another terminology here, x is always, it's customary to denote the input by x, and it's also customary to denote the output by y. Okay. And x is referred to as an independent variable, but y is called a dependent variable. Because it depends on the input, right? In the context of a function. All right, let's do a couple more. How about 25? So this is the domain, and this is the codomain. 1 is mapped only to 4. 2 is only mapped to 5. 3 is only mapped to 5. So is this a function? Yes, because every element here is uniquely mapped to an element in the codomain. Even though 5 is shared by multiple inputs, but remember, an output may be shared by multiple inputs, but an input may not be the same for distinct outputs, right? That's the essence of for a relation to be a function. 26. So this is, yes, it is a function. 26. 5 is only sent to -4. 6 is only sent to -4, and so on. So this is also a function because every element in the domain is uniquely assigned to an element in the codomain, even though that assignment is the same for all of them, but that's okay. Exactly like we discussed here in the lower part of problem 25. For 24, -3 is sent uniquely to 11, but -6 is not sent uniquely to a number in the codomain. It's sent to 13 and 9. So this correspondence is not a function, it's not a mapping, because it violates the uniqueness part. Correct? So 24 is not a function, but 25 and 26, they are functions. Okay, so how about 30? 30. Is y a function of x? So based on the relationship, this is an algebraic connection between y and x. You give me an x. To get the y, I chip away 4 units from my x, from my input, right? So no matter what x you give me, I chip away 4 units, I get the y. So for every x, there is one and only one y. So 30 describes a function, correct? 29, also same thing. For every input x, the output is unique. You give me x, I just add 3 units to it, I get my y, the output. So the y is uniquely determined by x. Okay? And for every x, you have a unique image y. Very good. How about 30? About 31? How about 31? Y is equal to x squared. So y is the output. Remember that in this discussion, y as a function of x. So you want to determine if y is a function of x. So the y is representing the output and the x is representing the input, right? Let me take this problem to the virtual board. So in 31, this is on page 147. So page 147, number 31, part A. The question is, let me go back to the question. The question is so you have y equals x squared. So you have y equals x squared. And the question is y a function of x? For every x, whatever the x is, you plug it in, right? So you have this function, this machine. You plug in the input, and what you get out of this is the square of that input, right? So just to be clear, this guy here is the same guy as the blue bullet, right? So that's input, that's output. You plug in the x, you get out the square of that guy x. That's representing the output y, right? That's the y. So do you see that this is actually a function? Because you give me this, I just square it, get out the output. There's no way I'm gonna get multiple outputs if I square a number, right? So this is a function. It is a function, right? So y is a function of x, to be more precise. So y is a function of x. Okay. Part B of the same question. What is it? Part B is x is equal to the square of y. So x is equal to the square of y. X is the input and y is the output, right? So let's copy this. So x is equal to the square of y. So remember, y is the output. Do we have for every input x a unique output? Well, if x is bigger than or equal to 0, right? It has to be bigger than or equal to 0 because x is the square of y, and if x is the square of something, that guy is certainly non-negative, right? So it's not if, it's actually an implication here. This entails, parenthetically, this entails that x is non-negative. One more time, why? Because if x is the square of a number y, then x is certainly non-negative. If you square anything, the least you get is 0, right? We discussed this above. Excellent. Then what? Based on a discussion that we had in the previous section, in the preliminary section, that's the same thing as, this guy is the same thing as what? Y is equal to plus or minus square root of x. Agree with that? So you get this. Remember this property, we recalled it in the previous video, but this stems, that property itself stems from quadratic formula, correct? So long story short, this guy here and this statement are equivalent. These two statements are equivalent. Okay, now it's clear that for a given x, you get two y's, right? Because this expression here, not expression, this equation is equivalent to this equation, or this statement, right? This equation is equivalent to this statement. So by equivalent, I mean they imply each other. So saying this or saying this, you're saying the same thing. All right, since you are saying the same thing, based on a property discussed last time, what do we have? What do we get? For every x you give this supposed to be function, you plug it in here and you plug it in here, right? And as such, you get two different y's. You get a y and you get its opposite, right? So for example, if you plug in 1, for x, one time you're gonna get negative square root of 1. What's square root of 1? It's 1. So you're gonna get y equals negative 1 or y equals 1. So you're gonna have two outputs for the input 1. One time negative 1, one time 1. As such, this is not a function because you get for every input, or there exists an input which has more than one output, and this completely violates the definition of a function, right? Let me take you back to this. You see here, to each element x in a set A, one and only one element in a set B. So to each input, you should have a unique output. If there exists an input which has multiple outputs, this is no longer a function, right? Okay, so back to here. So to summarize, or to conclude, this is not a function. This is not a function. back to the book. How about 28? So you have x plus 3 squared plus y plus 4 squared equals 1. So this is 28. So you have x plus 3 squared plus y plus 4 squared is equal to 1. Let me make sure I copied it right. So x plus 3 squared plus y plus 4 squared is equal to 1. Okay, so again, does this describe y as a function of x? Let's see, let's solve for y and see if we get multiple inputs, multiple outputs for that y. For a given x, do we get multiple outputs? So let's solve for y so that we see if for a given input we get multiple outputs, right? Like we did here. Okay, so I'm solving for y. I'm gonna bring all the x's to the other side. So that has to do with x. I'm gonna bring it to the other side. Whatever this package here, I'm adding it, right? I'm adding it. How do we undo the action of adding? We subtract. So if you subtract this package from the left side, you only get the y plus 4 squared. And if you subtract that package from the right side, you get 1 minus x plus 3 squared. Correct? Okay. And what? Look, according to this here, according to this, you're adding those two up. Each one of them is non-negative, and you sum them up, you get a 1. This means that each one of them is smaller than or equal to 1, right? Each package, you add two packages, each of which is at least 0, and you get 1. This means each of those packages must be at most 1. So 1 minus this package, which is at most 1, is at least 0, right? So my point is, this guy is at least 0. Correct? One more time. Why this is at least 0? It's implicit over here. You're adding this package to this package. Each of the packages is 0 or more, right? Because it's a square of something. So each package is 0 or more. You're adding them up, you get 1. What can you say? You can say that each package do not exceed 1. Correct? Do not exceed 1. If each package do not exceed 1, in particular, this is not gonna exceed 1. So this guy here, 1 minus the package is not gonna it's gonna be at least 0. Agree with that? Because the most this reaches is 1. Okay. Alright, excellent. So why do I care about this? Because I want to apply the property that we just discussed over here. What was the property? The property was, let me highlight it for you. So what's this property here? The property was, if b is non-negative, this is the one that we mentioned the other day in the previous lecture video. So if b is non-negative and you have a squared equals b, that's equivalent to saying that a is plus or minus square root of b, right? My point is, that's an overriding assumption, because I cannot run this program if b is negative, right? So that's my point. And that's exactly what I'm using here. That's exactly what I'm using here. Over here, the x was the b, and b, I needed b to be non-negative. It's right there. b is non-negative because b is represented by x. Over here, this package is representing the b. This package is representing the b. So I need b to be non-negative. I just made the case, right? I just made the case. And y plus 4 is going to play the role of a, right? So how about we call this property star, okay? I don't like the star. How about this? We call this property star, and we refer to it right here. So we refer to it right here. So we're gonna use property star right there. With property star has two ingredients, A and B, right? A and B. B must be non-negative. Who's gonna play the role of A here? A is the guy that's squared on this side, so it's the y plus 4. So the A in the star property is the y plus 4. And the B in the star property, right, is this whole thing. 1 minus x plus 3 squared. Which we just discussed. This is non-negative based on the discussion we just made before, right? Very good. Okay, so let's run this program, and we get that A is plus or minus square root of B. So A, which is y plus 4, is plus or minus this guy, the square root of this guy. So it's minus the square root of this guy. Correct? Or the A is gonna be plus the square root of this guy. Agree with this? I just copied. Plus or minus square root of B. A is plus or minus, right? There's a plus here. Plus or minus square root of B. Excellent. What are we after? Don't forget, we were after y. We were after y. Why? Because we wanted to determine if y is a function of x. So we wanted to check if for a given x we get a unique y. Apparently we're getting more than one y, right? Why? Because let's keep going. So this first equation is equivalent to saying that y is equal. I'm solving for y, so I'm subtracting by 4. If you subtract this side by 4, you only get y. If you subtract this side by 4, you get negative 4 minus the square root of 1 minus x plus 3 squared. Agree? So you get negative 4 minus this guy. Or you get y for this guy now, for this piece. You subtract also by 4. You get very similar thing to this, but instead of having the minus, you're going to have now the plus. So you're going to have negative 4 plus the square root 1 minus x plus 3 squared. Okay? And what does it mean? What does this mean? So if you provide me with an x for which the square root of this expression is meaningful, let's say minus 3 for example, if you replace x by minus 3, okay, you plug it in this machine, the output is gonna be what? Minus 3 plus 3 is 0, 0 squared is 0, 1 minus 0 is 1. So the output is gonna be here minus 4 minus square root of 1, which is 1, so minus 5. And also is going to have a different output. It's going to be minus 4 plus that thing which we just discussed is 1, and this is minus 3, right? So for the input minus 3, for example, which allows this expression to be bigger than or equal to 0, right? And hence the square root is meaningful here. So for this input minus 3, you get two different y's. You get one time y equals minus 5 and another time y equals minus 3. So is this a function then? So this is not a function, right? So this is not a function because for the input minus 3, for example, we got multiple outputs. So therefore y is not a function of x. Right? As we just saw, for example, if x is negative 3, y is minus 5, and y equals minus 3. So we can have two different outputs, right? Very good. All right. In fact, this is a circle, right? If you graph this equation, this is actually a circle. Let me. So this is a circle actually centered at -3 and -4. So it's going to be a circle. Centered at -3 and -4. And what we've done, and this is of radius 1, right? This is of radius square root of 1, which is 1. So the radius here is 1. Anyway, so it's not important. I mean, it is important, but that's not what I wanted to do. What I wanted to do is, I wanted to show you that if the input is at -3, you're gonna have two outputs. This is 1 and this is 2, right? This point here corresponds to input -3, so this is the -3 guy as an output, correct? So this guy here is -3 and this guy here is the -5. So you see, for this input -3, you have two different outputs. You have one output which is -3 and you have a different output which is -5. Okay, and pictorially, clearly this is not a function. We'll talk more about graphs I mean just shortly, but I just wanted to use this as a prelude. Okay, all right, let's go back to the book. And let's talk about problems from 35 through 56. Okay, so how about we do part B of number 35. So here you have a function f, which is given by this recipe, x squared plus 3x, and you want to evaluate f at -1. Okay, so let's write that down. So this is on page 147 again, and this is number 35. Okay, so 35 part B. Here you have f of x is equal to x squared plus 3x, and the question is find f of -1. Okay, so f of x is the image of the input x under the function f, so meaning whatever the x is, that's the recipe of the output. It has to do with x, and the input here happens to be -1. Okay. If you're not comfortable with the letter x or any other letter, how about a placeholder? So how about having a placeholder instead? Instead of x, I'm gonna write just simply a bullet. Okay, so the bullet is here, right? I'm squaring the bullet, and then I'm adding 3 times the bullet, right? 3 times the bullet. So this is times here. And who's taken the role of the bullet in my context? It's the -1, correct? So it's the -1 that's taken the role of the bullet. Okay, very good. Now that -1 is gonna sit here and here, and then I'm gonna copy. So it's gonna square, the function is gonna square that -1. If you would like to keep it orange, oops. if you want to keep it orange, just to highlight that this is actually the input, okay, plus 3 times that orange guy, which is -1 in this case. Okay, and what is that? -1 squared, remember we discussed this. This means I'm squaring -1. And if you square -1, it means you're multiplying -1 by itself. -1 times -1, that's 1. So that's 1. Correct? So that's 1. 3 times -1 is -3. So adding -3 is the same as subtracting by 3. And this is -2. Okay? So f of -1 is -2. Alright, let's go back to the book. How about now going for 36 part D? So what do we have? Actually, let's do 2 parts in 36. Let's do part B and part D. The function is the reciprocal of x. So g of an input is the reciprocal of the input, or multiplicative inverse of the input. I want to see g of -1 and g of half. Okay? Alright. So this is 36. In this context, I have the function g of x to be 1 over x. Okay? And I wanted to do, as I said, parts B and D. Let's start by part B. Let's start by part B. Part B is g of -1. Okay? So same thing. G of an input is 1 over the input, right? So this guy here is the input. Let's color it orange. And who's playing the role of that guy? It's -1. So that's the orange guy. And what is it? So what's g of -1? G of anything is 1 over the thing. G of -1 is gonna be 1 over that guy, -1. So 1 over -1, right? And 1 over -1 is -1. Correct? So if you plug in -1 in this function g, you get also -1, which is the reciprocal of -1, right? Part D. Now we're gonna evaluate g at half. So who's playing the role of my orange x? Is the half, right? It's the half who's playing the role of my orange x. So that's gonna be then 1 divided by my orange input, which is half. Correct? Okay. And now it becomes just purely algebra here at this point. The crucial step is obviously to know how the function operates. So this is probably the crucial step. That being said, some people still at this level struggle with how to handle this algebra. Let's explain it. What does this mean? This means I'm taking 1, that purple one, and I'm dividing it by this guy half. Agree with that? So one more time. The meaning of this fraction bar is division. So I'm dividing this numerator 1 by this denominator half. So I get this. And division is defined based on multiplication, right? If you want to divide by something, it's the same as multiplying by the reciprocal of the thing. And what's the reciprocal of half? The reciprocal of half is 2 over 1, so it's 2, right? So one more time. division and multiplication are intertwined. If you divide by something, it's the same as multiplying by the reciprocal of the thing. So the reciprocal of half is 2, right? Okay, so, and then what do we get? 1 times 2 over 1. What's 2 over 1? 2 over 1 is 2. So this guy is 2. 2 times 1 is 2, correct? I mean, it's not a surprise here. The reciprocal of half, we talked about it in the process. This means the reciprocal of half. The reciprocal of half is 2. Very good. Okay. So back to the book. Let's see. Let's do something that has to do with h. How about, you know what? How about 40? How about 40? So h of x is 5, and I want to determine what h of negative 7 is. Okay? So this is number 40. So you have h of x is equal to 5, and what they want is they want to evaluate h of negative 7. Correct? This is the question. Well, h of x is 5, meaning what? No matter what x is, the input, the output is 5. So the recipe of the output is ignoring what the input is. Correct? So the output is in the it's always 5 no matter what x is. So irrespective of the input, the output is always 5. Which means x has nothing to do with the input. X has nothing to do with the output. Actually, just look at the recipe of the output, which is this. You don't see x, so it's not an active ingredient in the recipe of the output. Correct? So whatever the input is, then the output is 5. This is like a dummy function. It outputs 5 no matter what the input is. Okay, so now if you plug in negative 7, we just talked about it. If you plug in negative 7, the output is gonna remain 5, right? Because again, the function, it's a dummy function. Actually, it's called a constant function. It disregards the input. It outputs 5 irrespectively of that input. So what's h of pi? H of pi is also 5. H of whatever is 5. Okay? Very good. Okay, so let's move on to this group here, 57 to 62, and let's do 60. So here the question is, find and simplify f of x plus h. Okay, so we want to find and simplify this output, and the recipe of f is f of x is 11 minus 5x squared. Okay, so this is number 60. Here you have f of x is equal to 11 minus 5x squared, and they want to evaluate and simplify, right? Find and simplify f of x plus h. Okay, so again, if we're not comfortable with the name x, because I see x here, it looks like what's going on here. So x here in this equation is representing the input of the function. If you're not comfortable with the name x as being the input, okay, so let's erase it and replace it by bullet. It's a placeholder, right? So let's replace it by bullet. The bullet is gonna sit right here, right? And this is understood to be a multiplication right there. Okay. So what's the question? The question is, if you plug in now this input, x plus h now is the input, right? That's the guy sitting between the parentheses. If you plug in this guy as an input, the question is, what do I get as an output? Obviously the output is going to have to do with the x and the h that are present in the input, right? The input is made up of the sum of x plus h. So this whole thing is one input. The sum is the input, okay? The input, we don't have two inputs. It's one input that's made up of two ingredients. And the input is x plus h, which is made up of x and h. All right. So f of anything is 11 minus 5 times the square of that thing, right? Well, over here the thing happens to be x plus h. So I get 11 minus 5 times the square of my input, which happens to be x plus h here. Okay. So I found it. This is the finding part. I found the output. Now the question is, simplify it. So I need to simplify this expression if I can. Well, the best I can do is I can expand this this expression, the square of a sum, x plus h, right? Back to algebra, beginning algebra or intermediate, I mean lower level than this, you just handle the square of a sum. And what's the square of a sum? What's the square of a sum? What is this guy? Well, the square of a sum is the square of one of them plus twice the product, right? Plus the square of the other guy. Correct? If you don't remember this property, you can actually develop it by hand again, because the square of x plus h means x plus h times x plus h, right? This is what x plus h squared means. Let's zoom in so we can see it better. This is what the square of x plus h means. It means x plus h times x plus h. And if you actually do it by hand, which means you are foiling, right? You're foiling. So what do we get? X times x is x squared. X times h is x times h. Plus h times x is h times x. Plus h times h. And h times h is a squared, h squared. Okay? And then I hope you understand that this and this are the same because multiplication is commutative, right? It doesn't matter in which order you multiply. If you multiply x first, I mean, if you write x first and then followed by h, or h followed by x, it doesn't matter in which order you do, they are the same, right? So these are the same. And they're equal to one of them. Let's say xh. So it becomes xh plus xh, which is 2xh. 2xh. And this is the x squared. And this is the h squared. Correct? So we get exactly this expression. Very good. Let me erase all of this. Okay. Alright, so let's zoom out. Now what? I can replace this package, the purple package, by this blue package and obtain 11 minus 5 times this package, which is the blue package, so x squared plus 2xh plus h squared, right? Okay, and then I'm not simplifying, I'm just expanding here. Now I can distribute the multiplication over addition, the two additions. So we get 11 minus 5 times x squared is 5x squared, minus 5 times 2 times x times h. 5 times 2 is 10, so 10xh. And then the negative 5 times the h squared is negative 5h squared. That's the best I can do. I mean, the question is simplify. Probably you could have left it like this, it's okay. But I expanded it so we kind of revisited a few algebraic concepts or algebraic identities along the way. Okay, it's good to revisit these from time to time. Okay, so, and I hope you see that the x and h are ingredients in the recipe of the output. That's the output, right? That's the output. The whole thing is the output if you input x plus h through the function f, right? Okay. Alright, so let's go to one more time to the book. And let's now go to those problems, 97 through 110. Let's choose 97, actually 98. I'm gonna try to do the even ones because you have the odd ones, the answers of the odd ones. So let's do let's do all of them, A, B, and C. Okay, so that's on page 159, 49, number 98. So part A, we have a function that's given by this. The name of the function is k. For a given x, it outputs x plus 6 divided by x minus 2. Okay? And what's the question? We forgot to actually look at the question. The question is, write the domain in interval notation. So we want to find the domain. What does domain mean again for of a function? Domain means it's the collection of all acceptable inputs through the function. Okay, so for this function k, the question is, what type of x can I plug in? Not what type. What are the real numbers that can be plugged in here instead of x? Remember, x is the placeholder for the input, right? So I copied it. What are the x's? What are the real numbers x that can be plugged in k so that this function doesn't produce an error? Okay, if this function is a machine, you plug in an x, you want the output to be produced. Once it's produced, you say that the x was accepted by the function k, because if it jams the machine, if the input jams the function, it should not be in the domain, it should not be accepted by the function, right? Alright, so what are the x's that can be produce an output through k? Well, the nature of the output of k is a quotient, right? It's a quotient between two guys, upstairs and downstairs. So you take the guy upstairs, which has to do with the input. You take the guy upstairs, which also has to do with the input, and then you divide the top by the bottom, right? So let's go to an abstract context, try to develop a mechanism on how to determine when a quotient is meaningful, when a quotient can be a real number. Let's call the quotient, the abstract quotient, n over d. N for numerator, d for denominator. When does n over d make sense or exists as a real number, right? When does n divided by d exist as a real number? Well, this happens precisely whenever you give me n as a real number, this is number one condition, right? N has to be a real number, so it has to exist, correct? Because if n doesn't exist, the whole quotient is not going to exist. So this guy has to exist. D also has to exist, right? Because if the guy downstairs doesn't exist, so you're replacing D by something that's not meaningful, so that the whole thing is not going to be meaningful anymore. And so it's an and here, right? And lastly, the guy downstairs, once you make sure it's meaningful, you cannot have it 0, right? Because if it's 0, we don't know how to divide by 0. So this is what it takes. This is what it takes for a quotient to exist, to make sense. One more time. A quotient is a real number. This is what I mean by exist. It's defined. It's meaningful. Okay. So a quotient is a real number if and only if three things happen. Number one, the numerator has to be a real number. Number two, the denominator also has to be a real number. And number three, the denominator cannot be 0. Okay? So this is what it takes. This package is what it takes for a quotient to exist. All right. So let me take this to the corner and let's give it a different color. Okay. So this guy here is going to be a reference for me. Great. Now back to here. K of x, I want to know for which x k of x exists, right? I want to understand what the domain of k is, which means for which x k of x, this output, which has this recipe, is meaningful. Well, k of x exists. I want to see if there are any constraints on x. K of x exists if and only if this quotient, because that's what's representing k, right? K of x. This quotient is meaningful, right? Correct so far? So k of x exists if and only if this quotient exists. And now I'm going to appeal to this discussion that allows me to understand when a quotient exists. When a quotient exists. Well, this exists if and only if three things happen. Let me take this further down. Three things happen. Number one, I want n to exist. Who's playing the role of n, by the way? It's the x plus 6. So, and who's playing the role of d? It's the x minus 2. So, number one condition is I want n to exist. So, n is x plus 6. I want x plus 6 to exist. Right? Number two, I want the denominator to exist as well. So, and number two, the denominator is x minus 2 to exist. And number three, you need the denominator not to be 0. Right? So I translated this abstract discussion to my concrete situation here by specializing the items n and d. The n happens to be x plus 6, the d happens to be x minus 2. Because this discussion here tells me when an abstract quotient is meaningful. In this particular case, I can assign roles for n and d and understand exactly what it takes for this quotient to be meaningful. It takes three things: numerator to be meaningful, denominator to be meaningful, and denominator not being 0. Alright, very good. Now, let's understand what it takes for x, because I'm after x, right? I'm after x. I would like to know what can x be so that the output is meaningful. So I'm after conditions on x. Alright. This first one, under what conditions x on x plus 6 is meaningful? Is there any x, any real number x, so that you cannot add 6 to it? Right, this is what it means for x plus 6 to exist. Is there any x, any real number x, so that you add 6 to it, it's not meaningful? Well, if you have a real number, you can always add 6 to that real number, right? So this guy here exists for all x, right? So this piece here, this exists if and only x. Okay, let me erase this. This exists for all x in R. Correct? One more time. The question is, under what conditions on x the output through k is gonna exist? Well, the output happens to be this quotient. So this quotient is gonna exist if and only if conditions 1 through 3 here are gonna be verified. I'm now dissecting what it means for each. I'm trying to place any demands on x so that all 3 conditions should be verified. The first condition, x plus 6, I need it to be meaningful. Under what conditions on x plus 6 is meaningful? With the understanding that x is a real number. Well, no matter what the real number x is, I can always add 6 to it. So as such, condition number 1 places no constraints on the input x, because condition number 1 is valid for all real numbers x. Okay? Moving on to condition number 2. Condition number 2 says your input in the function k should make this valid. What's this? The input minus 2 should exist. Well, is there any x you cannot chip away 2 units from it? Is there any real number you cannot subtract 2 from it? No. Any x, any real number makes this meaningful, right? The x minus 2. So this is also meaningful for all x in R. There are no constraints so far on x, right? Any x do this job, any x does this job. And the last condition in this package, x minus 2 should not be 0. Well, x minus 2 is not 0 precisely when x is not 2, right? That's the only time x minus 2 is 0. If you don't want it to be 0, you don't want x to be 2. So we get this. Okay? And now putting things together, recall the AND part here. So you want all 3 to happen. You want condition 1 to happen, and condition 2 to happen, and condition 3 to happen. Well, condition 1 places no demand on your input x, right? It places no demand. Any x is welcome, or any x makes property number 1 valid. Property number 2 also is valid for any x. But the last property here is only valid when x is not 2. So if you want all 3 to happen, the only demand is that x should not be 2. Okay? So we can just summarize this by saying x should not be 2, right? Because the first 2 conditions allow any x. The last one places a real demand on x. Very good. So now connect the 2 here. K of x, the output through the function k when the input is x exists if and only if the input is not 2. Okay? So any real number is allowed through this function except that guy. That's the bad guy 2. Okay? So now back to the question. What was the question again? The question is determine the domain of the function k and write it in interval notation. I'm gonna drop this part. You don't have to write it in interval notation. Just write the domain. You can use your own words, or you can use ways or ways to represent sets discussed in the previous section, in the preliminary section. So here x cannot be 2. X can be anything except 2, so that k doesn't jam, right? Okay, so let's write this. You write it using your own words. Therefore, the domain of k, how about we write the domain of a function d for domain, the subscript is going to be the name of the function. Okay, just a second. The name of the function, which is k in this case. So d sub k is the domain of the function k. So in this case, the domain of the function k is everything except 2, right? I'm going to write it like this. Remember the set theoretic difference? Everything, all real numbers, except the number 2. So this means all real numbers are part of the domain except whichever lives here, and that guy is 2. Make sense? If you want to write it, if you insist in writing this in interval notation, you can write it like this. So the domain of the function k is, in this case, all real numbers except 2. If you revisit the previous section, this means minus infinity all the way to 2, open, union, 2 plus infinity, right? This would be the writing of the domain interval notation. You can write it using this. You can use your own words. Doesn't matter to me. As long as it's correct, it's correct. Fine. So one more time, what does this mean? This means any real number between minus infinity to 2, excluding 2, is a good element or good input in the function k. I'm adjoining those good elements to another set containing good elements, and those elements are any number that comes after 2. So any number that comes before 2 and any number that comes after 2 is good. This means any number except 2 is good, as we discovered in the process and the analysis above, right? Very good. Now you're gonna tell me, oh, I always knew that. Why did we go through the trouble of talking extensively over, this concept when at the time I know that I just have to throw away what makes the denominator 0? Well, sure, that's correct, but look, this is a rational function. This is a quotient of 2 polynomial. This is why what you used to do is okay. But let me give you an example where what you used to do doesn't work anymore. For example, if I inject here a square root. Okay, so this is like a new problem. Let's call it a prime. Okay, it's a new problem. If I have square root upstairs, so if you tell me, okay, so I'm gonna apply the same thing. Whatever makes the denominator 0, I'm gonna accept it, but the function is gonna accept it. Well, which means that 2 is the only bad guy, right? Which means that 2 is the only bad guy. Well, how about you plug in -7? -7 is not 2 anymore. Is not 2, right? And -7, according to your discussion, should make the output, should produce an output. Well, let's check. If you plug in -7 instead of x, what do you get? Downstairs you get -7 minus 2, which is -9, so that looks great. But upstairs you get square root of -7 plus 6, right? And downstairs you get -7 minus 2, as we said, -9 downstairs, right? But then upstairs, what is that? Square root of -7 plus 6. That's square root of -1, right? And square root of -1 is nonsense. So this part is jamming. This is an error, right? This is an error. So the function is going to produce an error because a piece of it is an error. So there's no output then. So -7, which is different than 2, that 2 is the one that makes the denominator 0, is also a bad guy. So this -7 is a bad one. How is this translated in the analysis? Let's see where it's gonna pop up, right? Okay. Alright, so let me erase and discuss this new situation. I'm gonna keep everything now in red to go along with this. Same thing. So this remains a quotient. The output of the function k remains a quotient, and a quotient is existing, right? This quotient exists, is meaningful according to this, provided the numerator is meaningful, and the numerator now is this guy. The denominator is meaningful, and the denominator is not 0, right? Okay, so we have to tweak this part. We have to tweak because the numerator has changed in the new situation. All right, now let's understand what it takes for x, for this expression to be meaningful. This is no longer the case, right? What does it take for x so that the square root of x plus 6 is meaningful? If you remember the previous section, we recalled when the nth root is meaningful when the index, in this case 2, is even, right? Even umbrellas, even indexed umbrellas, I should say, only accepts radicands, which means the guys under the umbrella, should be bigger than or equal to 0. Should be non-negative, correct? So one more time, remember this: the nth root, when this is an even, when the index is even, the nth root of something is meaningful if and only if this guy under the umbrella, the radicand, is non-negative, right? This was discussed or revisited in the previous lecture video. Okay, and that's exactly the case. I have the even index. It's actually the 2, but we don't write the 2. And this expression is meaningful as long as the guy under the umbrella is 0 or more. Who's the guy under the umbrella in this case? It's x plus 6, right? So now this becomes equivalent. This thing becomes equivalent by this guy, right? Becomes equivalent to saying what? The radicand should be 0 or more. And who's the radicand? It's the x plus 6. So the x plus 6 should be greater than or equal to 0. Again, I use this package. Let me just change the color so it remains blue altogether. Okay. All right, one more time. The numerator, which is this, is meaningful as long as, based on this thing that we've recalled last time, in the last lecture video, as long as the radicand, which is x plus 6, the radicand is non-negative. So the x plus 6 should be non-negative. All right, and what does it take for x so that x plus 6 is non-negative? This means that x is -6 or more. Correct? All right, so the denominator didn't change, so condition 2 and condition 3, which have to do with the denominator, right? Do not or will not change in this case. All right, so to summarize, k of x exists, is meaningful as long as, this is our finding so far, as long as the x, the input, is -6 or more, and the input verifies this, and the input cannot be 2. Correct? So this is what we found so far. All right, you need all three to happen. Well, if you are asking for x to be negative 6 or more, and you are asking for x to be a real number, you're still asking x to be negative 6 or more. And the last part is x should not be 2. So what used to be the condition earlier in the previous situation, now we're gonna couple it with this, right? You're gonna also ask that x cannot be negative 6. Well, it cannot be less than negative 6. So x should be at least negative 6, right? So since you need all three conditions to happen, you need this to happen, and this to happen, and this to happen. If x is greater than or equal to negative 6, it's already a real number, so this is redundant. So it's the same thing as saying that x should be at least negative 6 and x should be different than 2. Okay? And the domain is gonna change drastically in this situation. It's not gonna be this anymore. What's gonna happen is I'm gonna accept all numbers from negative 6 onward, but since 2 is one of them and I don't need it, I have to throw it away. So since I'm gonna accept everything from 6 onward, negative 6 onward, and 2 is there in this guy, I'm gonna throw it away. So I'm gonna use the set theoretic difference to represent the domain. This is one way to do it. If you wanna use interval notation, that's gonna change also. What can we do? This would be, so anything from negative 6 to infinity except 2. So I'm gonna start at negative 6. I'm gonna go to 2, skip, adjoin everything that comes after 2, right? So this guy and this guy are the same. I hope this makes sense, and I hope you get to see the importance of the discussion that we just boxed here, right? You know, understanding exactly what it takes for a quotient to exist. Okay. All right. So as I promised you, we're gonna do parts A through C in 98. We did A and we created a new problem. Let's go back to the book so we can copy it. So now for part B, I have x plus 6 divided by x squared plus 2. This is j of x. So here I have part B, j of x is equal to x plus 6 divided by x squared plus 2. Let me make sure I copied it right. So j of x is x plus 6 divided by x squared plus 2. Okay, so still I need to find it or to determine the domain of the function, in this case j. Well, this is also a quotient, so this discussion in this bubble is still applicable, right? How about we copy it? How about we take it with us downstairs? Let's copy that. So I'm gonna still employ it. Okay, I'm gonna still employ it. Who's playing the role now of the numerator? The numerator is x plus 6. The denominator now is x squared plus 2. Okay, so j of x exists if and only if the quotient x plus 6 divided by x squared plus 2 exists, which is equivalent, according to the bubble, right? According to this discussion, equivalent to three things. Number one, the numerator has to exist, which is x plus 6. And number two, the denominator has to exist, which is x squared plus 2. And number 3, I need the denominator not be 0, and the denominator is x squared plus 2. Okay? Alright, now I need to unravel what each one means in terms of x. I need to see what type of demands, if any, is placed on x so that each of the conditions is verified. Okay, so let's check the first. X plus 6 exists. Well, if x is a real number, can't you add 6 to that real number? Sure, I just discussed it above, right? Whatever x is, I can always add the 6 to it, and as such, x plus 6 is always meaningful. So this exists for all x. For all real numbers x. Moving on to part 2. X squared plus 2. If x is a real number, I can always square it, so no constraints to square a real number. And once you square, you get a result. That result, you can always add 2 to it. So since this process works for any real number, this expression x2 plus 2 works or is meaningful for all real numbers. Okay. And finally, third condition, again, I'm trying to unravel what it means in terms of x. Does it place any demands on x? Yes or no? So x squared plus 2 different than 0. This is exactly the same as saying that x squared is different than negative 2. Correct? They are the same equations. Alright. If x squared is different than negative 2, if you want this to happen, what type of demands should you place on x? Well, one moment's thought shows that this happens all the time anyway for any real number x. Why? Because this piece here, this expression is 0 or more no matter what x is, right? No matter what x is. Correct? X squared is for sure non-negative. So there's no way it will reach negative 2, right? Because no matter what x is, you square it, you get 0 or more. Hence, there's no x which allows this expression to be negative 2. Make sense? So on the picture, x squared lives from 0 onward. X squared is here. Correct? X squared is 0 or more somewhere here, while the negative 2 is way here, right? So no matter what x, you are talking about x squared being in this blue region, and negative 2 is, there's a buffer zone between them, and it's not reachable. This pink point is not reachable by this expression, no matter what x is, right? Because this is true for all x. For all x. For all x in R, right? Does it make sense? This is why this equation here, or this demand, is not gonna place any conditions on the input x, because it's happening no matter what x is. Correct? All right. So let's erase this part then. So here, this means for all x. So this last condition, it looks like I'm placing a demand on x, but this turns out to be a demand that's not gonna require any constraints on x, because no matter what x is, this expression is never negative 2, and as such, this expression is never 0. Is never 0. Okay. All right. Very good. So to summarize, j of x, the output through the function j, if the input is x, exists, is meaningful as a real number, if and only if, based on our discussion, all 3 happens, and all 3, none of them places demands on x. Condition 1 doesn't require any demand on x. It's verified for all x. Likewise 2, likewise 3. So this means what? This means that j of x is going to exist if and only if x is a real number. That's it. This is the only demand, actually, x being a real number, which is understood. Okay, so any real number is welcomed by the function j. there is no x, there is no real number that jams the function, that's gonna allow the function to produce an error. Okay, so thus the domain of j, the function j, the domain of j is equal to all real numbers, the set of all real numbers. Make sense? Which is minus infinity to plus infinity. Remember this? Which is minus infinity to plus infinity. Okay. Alright, back to the book. So we did B, now we go to C. It's very similar, but now instead of having a plus here, I'm gonna have a minus. Okay. So I'm gonna actually write it on the same thing. Let me use a different color. About black. So part C, the change is that this is gonna be a minus, right? And the function now is no longer j, it's called p. It's called p. Okay. All right. So still, I mean, the same process. This is gonna be a minus. I'm tweaking what the discussion, I mean, what we discussed just before. This is gonna be minus, so this is gonna be minus, and this is gonna be minus, right? Okay. So the first thing is not gonna happen, is not gonna change. The second part, x squared minus 2. When does x squared minus 2 exist? Well, if you give me a real number, I can square it. Once I square it, I get a result, and I can subtract from this result 2. So no matter what x is, this process is working all the time. So x squared minus 2 exists for all x. And the last part, x squared minus 2 is not 0, right? X squared minus 2 is not 0 if and only if x squared is different than 2 now, plus 2. Correct? Then plus 2 now. And if x squared is different than, you want x squared to be different than 2, this means that x based on let me take you to this. Remember star? Do you remember star? This property that we talked about last time and in this video too. The square of something is equal to a non-negative entity if and only if that thing A is equal to plus or minus the square root of the non-negative entity. Correct? So back to our current slide or page. So we are now asking that x squared not equal to plus 2, which means so a squared is not equal to b, the b is 2 and the x is a, so x cannot be plus or minus square root of 2, right? So it cannot be plus square root of 2 and it cannot be negative square root of 2. Make sense? Alright. Now the function p exists if and only if all three happen. And what are these three things? This one, don't forget the and this one. Correct? So the first two conditions do not place constraints on the input x, but the last one does place two constraints on x. It cannot be plus square root of 2 and it cannot be negative square root of 2. So what do we obtain then? We obtain so x is a real number but not minus square root of 2. I'm gonna throw away those guys, right? So I'm gonna throw away the set from the whole thing. I'm gonna throw away the set consisting of two entities, the minus square root of 2 and the plus square root of 2. These are the two bad guys. And now in this case, dp, the domain of p, becomes, if you want to go with a notation, this is one notation. If you want to go with interval notation, so Okay, let me illustrate it via picture, maybe it would be easier. So let's highlight the bad ones. The bad ones are the minus square root of 2 and the plus square root of 2. Correct? These are the only bad ones. The good ones are everything else. These are good, these are good, and these are good, right? Meaning anything that's not the pink. How would we write this using interval notation? Well, it's going to be the union of three parts, right? The three green parts. This part is minus infinity to square root of minus square root of 2. This is this part. I'm going to adjoin to those good guys, which are between minus square root of 2 and square root of 2. Correct? Realize that I'm writing open sets, so I'm excluding the endpoints because the endpoints are actually the ones I'm skipping. So this part is those guys. This collection here is those guys. And I'm gonna join the last part, which is anything after square root of 2. So we obtain something like this. Okay. This is why I like the set theoretic difference way to represent, because I mean it's way neater than just writing this whole thing. Anyway, so I can't emphasize it more. Just use your own words to describe the domain. Okay, just be mindful about the fact that okay, people may ask you to write it in one way. Be mindful of that, but at the same time, please express your own way of representing things. Okay. All right. Back to the book. How about we discuss this quickly here? 102. Just very quickly. Let's talk about part B. M of x, the fifth root of x minus 3. That's different than square root, right? Because the index is 5, which is odd. And according to the previous discussion, previous lecture video, odd indexed umbrellas allow anything to sit under the umbrella, right? If you revisit the previous notes, the notes of the previous video, the preliminary video, odd indexed umbrellas allow any radicand to sit underneath it, okay? Which means for this guy M, x minus 3 can be anything. And if x minus 3 can be anything, x can in turn be anything, right? So bottom line, the domain of the function M and problem 102 is all real numbers, because this is an odd indexed umbrella. It allows any guy to sit underneath it. Okay, as long as the guy makes sense, obviously, and the guy here x minus 3 makes sense no matter what x is. Okay, all right. Let's go to 104 part C. 104 part C. So we have so 104 part C. We have t of x to equal x plus 1 divided by x squared minus 4x minus 12. Okay. All right. The nature of the output through t is still a quotient, which means I'm going to employ the same principle, right? I'm going to employ the same principle. So again, I'm going to take this, copy it, and place it here so you can be reminded of what I'm using. Very good. Who's playing the role of my n here? It's x plus 1. Who's playing the role of d? It's the whole denominator, this expression x squared minus 4x minus 12. And I'm gonna run this program, right? So t of x exists if and only if the quotient exists, because this is what represents t of x. And now via this guy, so probably the right place to place this guy is actually right there, right? So you get to see exactly what it's used. So I'm using it right here, okay? And let's color it entirely in pink. Okay, there we go. All right, so that's equivalent to saying three things. N, the numerator, should exist, and our n here is x plus 1. So x plus 1 should be meaningful. And the second one is the denominator, which is this guy, to be meaningful. And the last part is that the denominator, so this is part 3, the denominator should not be 0. Okay. All right. So when does x plus 1 make sense? When does x plus 1 make sense? When is it meaningful? No matter what x is, you can always add 1 to it. So x plus 1 is meaningful no matter what x is. So this is meaningful for all x and r. For the second part, x squared minus 4x minus 12, when does it make sense? So if I give you a real number, can't you square it? And if you square it, you're gonna get a result here. Save it. One more time. If I give you an x, can't you multiply it by 4 no matter what x is? No matter what x is, can't you multiply, as long as it's a real number, can't you multiply it by 4? So this works again for all x. So get the result. And then, can't you subtract two real numbers? This is meaningful, this is meaningful. Can't you subtract two meaningful things? Sure. And then, from that new result, can't you chip away 12 units? So the whole process works for all real numbers. Along the process, as you see, I didn't place any constraints on x. And as such, the x can be anything. So this is also working for all real numbers x. Okay. And finally, when does this expression meet 0? So I would like to solve actually the equation x squared minus 4x minus 12 to be 0 and then throw away the solutions of that equation. Well, x squared minus 4x minus 12, if you try to factor it using quadratic formula, and as I encouraged you in the previous video, you can revisit the quadratic formula concept in one of my lectures for a different course, but it's on my YouTube channel, so please visit that. And once you try to factor it, you're gonna realize that this is x plus 6 times x minus 2, right? You can always check by just actually it's the other way. It's plus 2 and minus 6, am I correct? Let's try. So x squared minus 4x, if I FOIL, x squared plus 2x minus 6x, so that's minus 4x. Minus 6 times 2 is minus 12. Okay, so with the help of quadratic formula, I can get this. I mean, if you have good enough intuition, these are nice numbers. So here the discriminant is a perfect square. Anyway, so you get this writing, and now what? This equation here, or the negation of this equation, becomes the negation of this equation, right? Because x squared minus 4x minus 12 is this blue thing, so it's right there. And if you don't want that expression to meet 0, so you don't want this product to be not to be 0. You don't want this product to be 0. All right. And when is a product 0? A product is 0 if and only if at least one of the factors is 0. So which means x minus 6 is 0. If you don't want to be 0, this should not be 0. None of the factors should be 0. So x minus 6 should not be 0. And x plus 2 should not be 0, right? None of them should be 0. And this means what? This means x should not be 6 and x should not be negative 2. Agree with that? One more time. I wanted to solve, let's say, this equation, x squared, or the negation of this equation. X squared minus 4x minus 12 not being 0. I factor this this expression as x minus 6 times x plus 2. So this equation became as this equation. The negation of that becomes the negation of that. And if you don't want the product to be 0, this means exactly that you don't want any of the factors to be 0, which means x minus 6 should not be 0 and x plus 2 should not be 0, which means x should not be 6 and x should not be negative 2. And now this guy, t of x, the output through the function t, is meaningful as long as, right, if and only if x can be anything here and x can be anything, this is condition 2, and x should not be 6 and it should not be negative 2. So put things together, you're allowing any x except those guys, correct? So this is what it means. So it follows that the domain of the function, what's the name of the function here, was t, is everything except those guys, negative 2 and 6, correct? I'm throwing away from the set of Ori numbers the subset consisting of just those bad guys, the 6 and the negative 2. Interval notation, I mean, we discussed it above, right? Remember, we talked about this discussion here. Now, one of them is going to be the negative 2 and the other is going to be the 6. So, it's the same reasoning. So, you get minus infinity all the way to minus 2, union negative 2 to 6, union 6 to plus infinity. Okay. Let's move now to a new concept. Let's read the following definition, which is about the graph of a function. If we have a function f with domain capital A, then we define the graph of the function f to be the set of ordered pairs that look like a comma f of a, where a is in the domain of the function, plotted in a coordinate plane. So, what's the graph? The graph of the function is this set, whatever the constituents of the set are, it's this set plotted in a coordinate plane, in an xy plane. Each constituent of the set is a pair of values. It's an ordered pair, which means the first spot is reserved for somebody and the second spot is reserved for somebody. It's an ordered one. It matters who sits where. The first spot, this spot, the left spot, takes the inputs, right? Takes points coming from the domain A. Okay? And the second spot, right, every ordered pair has two spots, right? One sits here, one sits here. So the one that sits here is an element coming from the domain. Let's call it little a. This guy lives in the domain, is in the domain of the function, which is capital A in this context. And the second one is not an arbitrary thing. It has to be the image under the function f, the image of that input A, of that guy A. Make sense? The collection of all of these makes up a set, and if you plot this set in an xy plane, then you give yourself the graph of the function f. So at the end of the day, the function is going to be the graph of the function is going to be something, maybe, I don't know, something like this. But each point here, I mean, this is a continuum, right? They are made up of this is made up of points. Each of those points look like a comma f of that a. Okay? So if this is the graph, of the function f, every point on the graph must be of this form: point coming from the domain, number coming from the domain, comma f of that number. Okay, very good. So in other words, let's read the three lines here. In other words, the graph of f is the set of all points a comma b, with the property that this b here is the image of the first element. Okay, so the second coordinate must be the image of the first under the function f for this point, and every point in the plane looks like x comma y, right? Every point looks like a pair of values. So for such a point in the plane to be on the graph of the function f, the second coordinate must be the image of the first, and the first must be an element in the domain. Okay? Alright, let's take a quick example. Let's sketch the graph of the function f of x equals minus 2x plus 6. So, you know from earlier courses, you know that this is of the form y equals mx plus b, correct? And if you plot these points, the x and y, if you graph this equation, you know it's going to make up a line. Okay? This is called the slope. I'm just giving you a crash course on this. This guy, m, is called the slope. Actually, this is not a crash course. This is like just recalling some just terminologies. So m is the slope. It dictates the amount of inclination the line is making with the x-axis. If m is positive, it's an increasing line, and if m is negative, the slope is negative, it's a decreasing line. B is the y-coordinate of the y-intercept. Correct? This is where the line is gonna cross the x-axis. Correct? Okay, so all what I mean here is we know that this is a line. We know that this guy is a line. This is of the form y equals mx plus b, and hence its graph is a line. Correct? So its graph is actually a line. Alright. Now, to fully determine a line, how many points do you need on the line? To fully determine a line, how many points do you need on the line? Well, You need 2 or more, right? If you only have 1 point on the line, you don't know what line you're talking about, right? We have infinitely many points, many lines going through a point. But if you know 2 points, on the line, you know exactly what line we have in mind, right? Correct? So what I'm gonna do is, in order to graph the function f, which I know ultimately it's gonna be a line, it suffices for me to find 2 points on the line. And for me to find 2 points on the line, which is the graph of the function f, I need to find pair of values that are of the form a comma f of a. Agree with this? Because every point, according to the definition of the graph of a function, every point on the graph of the function looks like a comma f of a, where little a lives in the domain of the function. Okay? So, for this function, what's the domain? The domain of this function is all real numbers, because no matter what x is, minus 2 times that number is meaningful. Once you get the result, you add 6 to it. This can be done for all real numbers. So the domain of the function f is all real numbers. So the domain of f is the set R, right? The set of all real numbers. So the function is everywhere defined. No matter what x you plug in, you're going to get an output. Okay? It suffices to actually determine the graph, as we just discussed. You only need 2 points on the graph, because this is a line, and 2 points fully determine a line. Let's give ourselves 2 points on the line and then find what that line is. Any point looks like an element from the domain comma f of that element, and the domain is all real numbers, so I can choose any number a that I want. Let's choose simple ones. How about a equals 0? So when the input is 0, when the input x, because the input is represented by x, when the input x is equal to 0, the output, let's call it y, it's again customary to call the output y, is equal to f of 0, right? F of 0, which is, what's f of 0? F of 0 is negative 2 times 0 plus 6. What's negative 2 times 0? It's 0. That's 0. Plus 6 is 6. So, out of this bullet here, this discussion in this bullet, the point 0 comma f of 0, which is 6, is on the graph of the function. Correct? Do you agree with me? So again, every point on the graph of the function looks like a comma f of a, and a lives in the domain of the function. Little a lives in the domain of the function. The domain here is R, so you can choose any number. I'm choosing 0, so the second coordinate must be f of 0. So the second coordinate must be f of 0. I computed what f of 0 means. It's simply 6. So a comma f of a, in this case 0 comma f of 0, 0 comma f of 0, but f of 0 is 6, is on the graph of f. Okay? Alright, that's one point. Now I need the other point. I need another point. I have infinitely many points to choose from. I need another point so that I can fully determine or graph the line. Let's choose another one. How about 3? So when the input x is 3, you can choose any number, okay? When the input x is 3, you can choose any number in the domain, but the domain happens to be everything, so you can choose any number. When the domain x is 3, f of 3, the output, so the output y is gonna be f of 3. And what's f of 3? F of 3, you plug in 3 for x, right? And it's gonna sit here. 2 times 3 is 6, so negative 6 plus 6, so 0. So it's gonna be negative 2 times 3 plus 6, which is negative 6 plus 6, which is 0. Correct? So when the input is 3, the output is 0. So what can you infer? Another point on the line is, any point looks like a f of a, so in this case it's gonna be 3 comma f of 3, which is 0. 3 comma f of 3, which is 0, is on the graph of f. Okay. Agree with that? So one more time, those guys, this guy here is the image of the first coordinate, which is 0. This guy is f of the first coordinate, which is 3, right? For this pair of value, for this point in the plane to belong to the graph of the function, it has to look like a f of a, 0 f of 0, 3 f of 3. But we concretely evaluated each of those images, and one happens to be 6 when the input is 0, and the other happens to be 0 when the input is 3. So now those 2 points, 0 comma 6 and 3 comma 0, are 2 points on the line. So now I know exactly what the line looks like, what the graph of f looks like. Let's see. So I have, this is, say, the y-axis, and this is the x-axis. So I have the 2 points 0 comma 6 and 3 comma 0. So 0 comma 6 happens to be 0 comma 6 happens to be, say, here. That's the point 0 comma 6, right? And the other point, which is 3 comma 0, happens to be somewhere here. So 3 comma 0 is somewhere here. Okay. And now I know exactly what the line is. It's just the line that passes through these 2 points, right? So, alright, I'm gonna try to fit it. So something like this. Okay. Alright, you know what? I'm gonna erase this dot and redraw it here. There we go. Okay, so that's the graph of the function f. So this guy is the graph of the function f, given by this recipe, correct? Given by this recipe. And each point, this line is made up of infinitely many points. Each point is of the form a comma f of a. Okay. For example, this point, say, this point here, maybe it's like, I don't know, 10 comma something, right? But this thing has to be f of 10. Correct? To be more precise, what's f of 10 in our context? F of 10 is when x is 10. F of 10 is negative 2 times the 10, so negative 20 plus 6. Negative 20 plus 6 is negative 14. So this guy here is negative 14. Right? So the y value is negative 14. So this point, which belongs to the graph, has 2 coordinates, 10 and negative 14. Okay. 10, negative 15 is below this, but it's off track. It's off that line because negative 15 is not the image of the input 10. Okay, so this is a concrete example of the previous definition. Every point on the graph of a function f looks like point coming from the domain, comma, f of the point, f of that point, right? And this is by definition of the graph of the function. Excellent. Now, a natural question is, which curves in the xy plane are actually graphs of functions? For example, if I give you a graph, if I give you an xy plane, something like this, say, and I give you a curve, a curvature, or a graph, some graph, okay, something like this. Can this be the graph of some function? I'm not saying find the recipe of the function, but if it exists, I'm saying, can it be the graph of some function? If it is the graph of some function, by definition of a function, remember the very first page in this section, a function is a rule that maps every element in the domain to a unique element in the codomain. Okay, so every input should have a unique output. Well, according to this graph, if this were to be the graph of some function, every point should be of the form a comma f of that a, right? Correct? And f of that a, f of the a, which and little a lives in the domain of the function, f of that a is one element, is one number. It cannot be multiple numbers. Okay, so the output, which is f of a of the input a, should be unique. If you take a moment here and you realize that you make the following observation. If you take this input, let's call it, I don't know, t. If you take this input, according to the picture, it has three outputs. The first output is this, right? The second output is maybe this, and the third output is maybe this. Correct? So if this were to be the graph of some function f, each of this point is gonna look like t comma f of t. Correct? Because that's what it takes for a pair of values, for an ordered pair of values to be on the graph of a function. It has to be a number and its image. According to this picture, those 3 points must be of the form t, that number that we labeled as t, comma f of t. Each one of those is gonna have those 2 pair of values. Clearly then, this number f of t, which is depicted by this bullet, the height of the bullet here, is different than this f of t, the height of this bullet, and which in turn is different than this, the height of this bullet, f of t. So these 3 guys are different, which means t is assigned to 3 different outputs. This is the height of this point is the first output, the height of this point is the second output, and the height of this point is the third output. So this number t, via this assignment or correspondence, is mapped to 3 different things. 1, 2, 3. So can this be a function? Obviously not. It violates the definition of a function because every input must have a unique output. So to summarize, for a given graph, to have a chance to be the graph of some function, every input should have a unique output, which means if you are located anywhere on the x-axis, you should look up or down and do not see the function more than once, right? If you stand here, you see it at 3 spots, 1, 2, and 3. Correct? As such, this cannot be the graph of any function. Alright, so, and vice versa. So this statement that I just mentioned is an if and only if statement. The way the way books write it is, standing on the x-axis means you can take a vertical line. You can take a vertical line, say, and if you find some vertical line that passes through the graph of that through the given graph more than once, then certainly that graph is not the graph of any function, because if a graph is if it crosses more than once, it means that for one input, for one location, you have different y values, different outputs, and as such the correspondence is certainly not a function because it completely violates it. Okay, so that's the vertical line test. What comes next here? So let's read it. The vertical line test states the following: a curve in the coordinate plane is the graph of some function if and only if no vertical line crosses or intersects the curve more than once. It's okay if it doesn't cross it. If it doesn't cross it, it means that the function is not defined there, right? If I give you a function that looks like maybe just from this point to this point, right? There is no vertical line here that passes this graph more than once. But there are vertical lines like these that do not pass or do not cross this graph. This is okay because what this means is this function only accepts input that are between here and here. This would be the domain of the function. This would be the domain of the function. Okay, graphed in green here. If you take a line that doesn't cross, it's fine, but it should not cross more than once. If it does cross more than once, then as we saw above, the function cannot be, the graph cannot be the graph of any function. Okay. All right, so let's take a few examples from the book. Let's go back to, let's say here, I don't know, how about this, 19, or you know what, let's do 17. Can this be the graph of a function? No, because this graph fails the vertical line test. There exists a line, a vertical line, namely, let's say the y-axis. There exists a vertical line, namely the y-axis, which crosses the graph more than once. It crosses it 3 times. 1, 2, and 3. So which means the input 0 have 3 distinct outputs, and certainly this cannot be the graph of a function. 18. This graph, can this be the graph of a function? Yes, because there is no location, there is no location for a vertical line that crosses the function more than once. By the way, when they put like arrow here, it means that the function keeps blowing up like this, and arrow here means the function is blowing down like this, right? So, but and for this graph, there is no vertical line that passes the graph more than once, and this is the graph of a function, of some function. I don't know what function, but there exists a function which has this graph. How about 19? the graph is horizontal, completely horizontal line. As such, there's no vertical line that crosses this graph more than once. Okay, any vertical line here crosses it exactly once, and as such it passes the vertical line test, and hence there exists a function which has this graph, right? There exists a function which has this graph. Namely, the function here is what do you think? The output is always 2, right? No matter what the input is, the output is always 2. So this is the function, let's say f of x equals 2. Okay? But the essence is there exists some function by the vertical line test that has this graph. In this case, it's easy to know what the function is. It's the function f of x equals 2, because the output is 2 no matter what. Look, the output is always 2. All right, 20. Can this be the graph of some function? Well, run the vertical line test. Is there a vertical line? Is there a vertical line that passes this blue graph more than once? If you take a vertical line here, it doesn't cross, so far so good. But if you actually take the vertical line that coincides with the graph of that, the blue graph, it crosses it infinitely many times. In particular, it crosses it more than once. So as such, this graph cannot be the graph of any function. Correct? This is not the graph of any function. Alright. How about 21? When they put bullet, it means that the function is defined there. And when they put hole, it means that the function is not defined there. Let me take actually this graph and discuss it on here. Okay, so it's too big. Alright, which problem is this? This is on page 146, number 21, right? So that's page 146, number 21. Okay. All right, so the graph is just made up of these steps. What is this point? This point here. This point has two coordinates, -3 for the input and 3 for the output, right? So -3 comma 3, sorry, -3 and -3, so -3 comma -3 is this point right there, right? Okay. How about this point here? This point here is -2 comma -3. -2 comma -3. This point here is not part of the graph. When you see a hole, not a disk, when you see a hole, it means that the function gets close to that point but doesn't reach it. So what's this point? This point is -1 comma -3, but the function doesn't reach that point. So the input -1 doesn't have this output. It has this output. So the output for the input -1 is simply -1. Correct? So because this is a hole, it means that the function doesn't reach this point. It gets close to it. The function stays, it gets close to that point but doesn't reach it. When the input is smaller than -1 and bigger than -3, when the input is somewhere here, if you give me an input here, the output is always on this blue line. The output is always -3. Okay? But if you reach the input -1, the output is no longer here. That's the presence of the hole. The output is actually right there. So if the input is -1, the output is -1. It's that depth. Okay. Similarly here, if you give me any point, any input between -1, including -1, and all the way to 1 excluding 1, the input remains -1, right? The output remains -1. So one more time, no matter what the input is between -1 and 1, including -1 excluding 1, the output is -1. But once you reach the input 1, the output becomes here, which is 1. So f of 1 is equal to 1. Okay. What's f of 2? Input 2. So on this graph, is there which point has first coordinate 2? That's the point which has first coordinate 2. Correct? This is for the input 2. What's the output? It's this height. And what's this height? It's 1. So f of 2 is also 1. Correct? And so on and so forth. Alright, now back to the question. The question is, can this be the graph of some function? Let me erase all of this. Can this be the graph of some function? Yes, because there exists no vertical line that passes this graph. The graph is made up of these pieces that passes this graph more than once. This is a vertical line. This is a vertical line. It doesn't pass, so far so good. It doesn't cross the graph. This one crosses it exactly once. Any one in between also crosses it exactly once. How about this vertical line? How about this vertical line? The longest one that I just drew, longest segment. This vertical line apparently it crosses it more than once, but don't forget, this means a hole. A hole means the function doesn't reach this point. And as such, the only intersection between that long segment, vertical segment, and the blue graph is simply here, right there. That's the only intersection. Okay? Similarly, if you take a vertical line here, this line, this red line or brown, doesn't cross the blue graph more than once. It actually crosses it exactly at this point, because this point here is not part of the graph. There's a hole. Okay, and so on and so forth. So long story short, there is no vertical line. There is no vertical line that passes the function more than once, and hence it passes the vertical line test, and as such, it is the graph of some function. Correct? So it is the graph of some function. So there exists a function which has this graph. Okay, so I'm gonna just say see explanation in the video. Okay. Alright, so how about 22? The difference between 21 and 22 is obvious. I don't have holes anymore. I have bullets, right? Which means the function or the assignment, the correspondence reaches those endpoints now. So now if you take the vertical line, let's say the one that goes through -1, right? If you take this vertical line, certainly this line crosses the graph, the blue graph, more than once. It crosses it one time here, and it crosses the other time here. So there exists at least one position for the vertical line. There are many positions actually, but once there exists one vertical position, one vertical line that crosses the graph more than once, this graph cannot be the graph of any function. Okay, so this is not the graph of any function. All right. Okay. How about those numbers from 63 to 70? Refer to the function f, which is made up of these pair of values: 2, 3, 9, 7, 3, 4, negative 1, 6. The understanding is this function, if you plug in 2, you get out 3, right? So f of 2 is 3, f of 9 is 7, f of 3 is 4, and f of negative 1 is 6. Okay, so I'm gonna do this quickly. Determine f of 9. So which pair of values here has 9 as its input? Because f of 9 is the output when the input is 9, right? So which pair of values here has the input 9? It's this guy. When the input is 9, the output is 7. So 7 is the image of 9 under the function f. So 7 is f of 9. So f of 9 is 7. Okay? Alright, how about f of 2? F of 2. Well, you go to the pair of values whose first coordinate is 2. The second must be f of 2, right? The second must be f of 2. Well, that's the pair of values whose first coordinate is 2. Then 3, that guy 3 is gonna be the image of 2 under the function f. So 3 is f of 2. Alright. Okay, so 70. For what values of x is f of x equal to 4? So for which input it's the output, right, is 4. For which input the output is 4. For which x is f of x 4. So which input correspond to output 4? Take a look. Output means second coordinate. I have only one pair of values whose second coordinate is 4, namely this pair of values. So 4 is the output. If you plug in 3, then you get out 4. So if you take x to be 3, then f of 3 is gonna be 4. Okay? So the only x that allows the output to be 4 is actually 3. Alright, let's do one more. How about this? 69. For what values of x is f of x 3? For what value or values of the input is the output 3? The output is 3. Is it this one? No, this is the input. It's that one. That's the output 3. So for this output, it suffices to enter 2 as an input in the function to get the output 3. So f of 2 is 3, right? So if you plug in input 2, you get out output 3. So for this problem, for what values of x is f of x 3 is for x equals 2. Okay? Alright. Determine the domain and range of the function. Alright, let's take a couple of these. Let me take this picture. This is number 87. Okay. Let's paste it here. So this is number 87. Let me just make a small arrangement. Okay, I'm shifting everything up just to make room. Okay. So this is number 87. Okay. 87. Oops. The question is find the domain and range of the function given by this picture. So what's the graph of this function? It's simply those points, right? How about we take a moment to label those points? What's the first one? What's this one say? This point, to be on the graph of the function, it must be the first coordinate must be in the domain, and the second one must be in the range. Actually, the second one must be the image of the first, correct? So this point has the first coordinate -3, and the second coordinate, which is f of -3. I know that for as a fact because this point is on the graph of the function, so the second coordinate certainly is f of the first. But what's that height? What's the y coordinate of this point? It's 4, right? Okay, so f of -3 is 4. Make sense? So let me change the color of this guy. Okay, very good. Let's try again. How about this point right there? This point has the first coordinate 3. Since it belongs to the graph of the function, the second coordinate certainly is the image of the first, so the second coordinate is certainly f of 3. And what's f of 3 in this context? It's this height. And how much is the height? It's 5. Okay? So f of 3 is equal to 5. And so on and so forth. Let's actually do all of them. This one here has coordinates 2, -4, right? Since it belongs to the graph of the function, you know for a fact that this guy is f of 2. Right? Because this is what it takes for a point on the plane to belong to the graph of the function. The second coordinate must be the image of the first. How about that? This one has first coordinate -2 and second coordinate -3. Since it belongs to the graph of the function, you know that the second coordinate is f of the first. So this guy is f of -2. Okay? So what's f of -2? F of -2 is 3. And finally, this point here, it has also two coordinates, -1, 3, and the second coordinate, which is 3, is nothing but f of the first one. Okay? Alright, so now the domain. They asked us to find the domain and the range. Let's start with the domain. The domain is the collection of all acceptable inputs through the function. And according to the picture, the only accepted inputs, remember inputs are the first coordinates, the only accepted inputs through the function are the first coordinates of those points, right? Those 5 points. So -3, -2, -1, 2, 3, right? So they are only the first coordinates, -3, -2, -1. I'm talking about just the first coordinates, 2 and 3. Make sense? For the range by definition means the collection of all the outputs when you vary the inputs, right? So this is the collection of all the possible outputs. What are the possible outputs? So they are the y coordinates, 4, 3, 5, -3, and -4, right? This is the range. Let's write them in an increasing fashion. So -4, -3, the y values, -4, -3, 3, 4, and 5. Okay, so this is the range. Alright, let's do another one. How about I should have done 88. I got excited about 87 because you have the answers for the odd, so I keep forgetting. Alright, let's do 90. Okay, so now I'm doing 90. Alright, so still I need the domain and I need the range of this function, right? They told us it's a function. Okay, so what's the domain? Domain is the set of all the accepted inputs through the function, which means they are all the first coordinates of the points on the graph of the function, right? The first coordinates. So think about it. Take a moment, pause the video and do it. So if you stand anywhere here, remember this means it keeps going down, right? It blows down. The function keeps going down. This is what the arrow means. Here there's no arrow, which means it doesn't go beyond this point. The function doesn't even reach the point, right? Okay. So if you stand anywhere on the negative side of the x-axis, right? If you stand anywhere here on this side, let's say if you stand between minus infinity and minus 2, you can always find a corresponding output, right? It's a negative number all the time, correct? For example, if you go to minus 4, if you plug in negative 4, the output is also negative 4, right? It's that depth of this y, of the y coordinate of this, it's the y coordinate of this point, okay? If you give me minus 3 as an input, the output is minus 2, right? It's the y coordinate of this point. All right, so any point here, any input that comes from this side of the x-axis always has an output. So all these guys should be in the domain of the function. Okay, how about minus 2 itself? If you plug in minus 2, where's the output? Well, that's the point which has first coordinate minus 2, right? This is the point whose first coordinate is minus 2 that belongs to the graph of the function. And what's the y coordinate of this value, of this point? Is 0. So what can you say about the y coordinate or the output of the function when the input is negative 2? Is 0, correct? 0 is f of negative 2. Because remember, the second coordinate of a point on the graph of the function is the image of the first coordinate. So if the first coordinate is negative 2, the second is going to be f of negative 2. In this case, apparently is 0. Alright. And so minus 2 is part of the domain because the function produces an output for this input. And so on and so forth. You can keep going. So all these guys are in the domain, right? Negative 2 is in the domain. How about a guy here? This also is in the domain because the function produces this height as an output for this given input. Okay, and so on and so forth. So all these points also have outputs. If you give me this input, that's the output, right? This height is the output. So for example, 1.2 has 3 as an output, right? So all these points have outputs. You can get as close to 4 as you like, but you cannot reach 4. You cannot reach 4 because 4 doesn't have an output, right? There's a hole here. You might think, okay, this is the output, but this is not a point on the graph. So 4 doesn't have an output, but any point to the left of 4 has an output. So what's the domain of the function? The domain of the function is all real numbers that are smaller than 4. any number you give the function less than 4, the function is going to produce an output. Okay, so minus infinity all the way to 4, excluding 4 as we just discussed, because I have a hole here. Make sense? Alright, so another way, I mean, can you find a way to remember, or easy way to find the domain of a function given its graph? So technically what we're doing here is we are projecting all these blue points onto the x-axis, right? So we're kind of like flattening the function along the x-axis, right? So if you project all the points onto the x-axis, which means you only care about the x-coordinates of these points, so you project them orthogonally, you just drop them, you're gonna only see this purple part of the x-axis, and that's exactly the domain. Okay. All right. Now for the range, let me just erase this, all this. For the range is the collection of all possible outputs through the function, right? Which means the collection of all the y values of the points on the graph of the function, right? Because the y values of the points on the graph of the function are the possible outputs, right? So the question is, what's the range? What's the collection of all the y values of the points on the graph? Well, it's very much the same as domain, but now we're kind of like projecting all the points on the y-axis to retain the y coordinates of those blue points, correct? If you project all these points on the y-axis, well, this point, for example, projects here, so this is a possible output. The function produces this output, right? If you project all these guys onto the y-axis, you're going to see all this part of the y-axis, right? All these points, if you project them onto the y-axis, you see all this part, correct? So any y value that's orange is reachable through the function as an output, okay? And how about here? Yeah, if you project all these points, which means you retain the y values of these points, so you get this part of the y-axis. If you keep projecting, you keep getting those y values, and the last y value you get is this guy, 4. 4 is the last, or is the highest y value the function can produce. Is the highest output that the function can produce. Namely, if you plug in 0, right? If you plug in 0, you get the output 4. Correct? Because this point has two coordinates, 0, 4. Remember that? So 0, 4. That's the y coordinate of this point. These are the coordinates of this point. So the y coordinate is f of 0. So 4 is f of 0. So if you plug in 0, you get 4 as an output. Alright. Are gonna tell me, oh, how about these? But we already accounted for the outputs represented by, or the outputs or the y coordinates of these blue points, correct? So all these points have output 3. I already accounted for this, and all these points have outputs between 3 and 4, which I already accounted for that too. So long story short, this is the range of the function y. So this is how much the function allows us to see from the y-axis. It's missing a huge chunk, but it's only allowing us to see this. In contrast with the blue, I mean, if you go back to the beginning of this video, we talked about the dark room, and you turn the flashlight on. The dark room is the y, the ambient space is the y-axis, or line. And the flashlight, the function here in this context, allows us only to see this piece of it. So from minus infinity all the way to 4. So from minus infinity all the way to 4, but this time including 4, right? Because 4 is a possible output. Makes sense? Okay, let's do more of these. Okay, how about 96? Let's take this. 96. Okay. So still, we're talking about the domain of this function, and we're trying to find the range of this same function. Alright, the domain of this function, which means the collection of all the first coordinates of the points that belong to this graph. Well, those points, if you project them onto the x-axis, what do you see? If you project all these blue points, remember this hole is not a blue point. If you project this thing onto the x-axis, you see -4, right? -4 is a possible input because this point has first coordinate -4 and it's part of the graph of the function. You see all of this, and this doesn't drop because I have a hole here. So I have a hole. So this purple segment here is the projection of the blue points onto the x-axis. Now, how about the projection of these blue points onto the x-axis? This point drops, it's gonna fill in this hole, and it's gonna, all these points are gonna drop, and I'm gonna have a new hole here, right? So far, if you plug in any number from -4 all the way to 2, excluding 2, if you just focus on these two branches, if you take any input from -4 all the way to 2, excluding 2, it has an output. For example, if you plug in -1, the output is 1. Okay, the output is not 4, it's 1. Okay, let's keep going. We're still missing the first coordinates of these points. This point, you drop it on the x-axis, is gonna fill in this hole, and it's gonna keep going the same fashion with a hole at the end. Correct? So it looks like the domain of this function is everything from -4 all the way to 5, excluding 5. If you give me any input from -4 to 5, excluding 5, I'm gonna be able to give you the corresponding output. F of 5 doesn't exist, right? Because the function, look, at 5, if you look up, you don't see the function. If you look down, you also don't see the function, because this is a hole, right? Okay, so what's the domain? It's from -4 to 5, excluding 5, including 4, right? Okay. Now the range. The range of this function. So the range is the collection of all the possible outputs, which means the possible y values, the collection of all the y values of these blue points. Okay? So all these blue points here have a common y value, which is 4. Correct? So if you project all these points onto the y-axis, you only see the 4. All these points, no matter what the input is, the output is always 4. Now, all these points have a common y value, which is 1. And all these points have a common y value, which is -2. So there are 3 possible outputs for this function, no more. The output is either -2, 1, or 4. The output is -2 if you give an input between 2 and 5, excluding 5, including 2. The output is 1 if you give an input between -1 to 2, excluding 2, including -1. And the output is +4 if the input is between -4 and -1, excluding -1, including -4. Okay, so there are only 3 possible outputs through this function. So the range is going to be a discrete set, which means I'm going to be able to actually enumerate the elements in this set. So as we said, there are just three guys, -2, 1, and 4. Okay. All right, so let's go to the next concept here. The last definition in this section. So what do we mean by x-intercepts of a function? The x-intercepts of a function f are the points where the graph of f crosses the x-axis. So if this is the x and y axes, so if this is the xy plane, okay, and the function makes a dance, let's say here, I don't know. So those points where the function crosses the x-axis are called the x-intercepts. Okay, so these green points are the x-intercepts. And the y-intercept of a function is the point where the function or the graph of the function crosses the y-axis. So this point here is the y-intercept. Okay. All right. So a quick comment here. We may have multiple x-intercepts for a function, right? We may have multiple x-intercepts, but we have a unique intercept if it exists. So we may not have y-intercepts. Why? We may not have many y-intercepts. We only have either no y-intercepts or one intercept, y-intercept. Why? Because the y-intercept is where the function crosses the y-axis. If we have multiple y-intercepts, which means that thing is going to cross multiple times on the y-axis, as such, it doesn't pass the vertical line test. So it cannot be anymore a function, right? So we have at most one y-intercept, and we may have many x-intercepts. Very good. Now, how do we find the x-intercepts? How do we find? Let's find a way to actually determine algebraically. This definition is purely geometric, right? It has to do with just geometry. How do we find algebraically the x-intercepts? Well, let's take a look. Let me blow up this a little bit. So what's common to all these green dots? This one, and this one. They belong to the x-axis. So, I mean, there's a feature exhibited by all points that belong to the x-axis. What's that feature? They all have the y-coordinate 0, right? They all have the y-coordinate 0. Correct? Because they are on the ground, and the y-coordinate is 0 because they're not away vertically. All right, and this is number 1. Number 2, they also belong to the graph of the function. Let's call the function f. They also belong to the graph of the function, right? So if the first coordinate is t, this one has to be f of t, because this point belongs to the graph of the function, and we know from the definition of the graph of a function, the second coordinate must be the image of the first. If this guy is z, the second coordinate is f of z. Correct? If this guy is w, this guy has to be f of w. Correct? So how can we translate this then into algebra? Well, we're gonna say the following. To find the x-intercepts, what should we do algebraically? We're gonna try to find for which values, we're gonna find these guys, right? For which values f of x is equal to 0, right? We're gonna, in this case, x happens to be t, z, and w. So to find the x-intercept, we solve the equation f of x equals 0. Agree with that? So all the solutions of this equation are gonna be those first coordinates. Makes sense. For example, for instance, you know what, let me take you back to an earlier problem. How about this one over here? What do we have? We have the graph f of x equals minus 2x plus 6. How do we find the x-intercept? We just discussed it on the other page. We solve the equation f of x equals 0, right? So we solve the equation f of x equals 0. And if you solve the equation f of x equals 0, let me do it right here. If you solve the equation f of x equals 0, this means you are solving the equation negative 2x plus 6 equals 0, right? Because this is what f of x means. And if you solve for x, you're gonna realize that you are finding what? So negative 2x equals negative 6, which means that x, you divide by negative 2 here, you get 3, correct? So this means when x is 3, the y is 0. So 3 comma 0 is the only x-intercept for this function f. Okay, because algebraically we didn't find any other x that solves the problem, that solves the equation f of x equals 0. Correct? And this is interpreted also geometrically, which we found before. That's the point I was talking about. Okay. All right. Let's go back to this page. So this is how we find. This is how we find the. We find algebraically the x-intercept. How about the y-intercept? How about the y-intercept? Like this one here. Let's use a different color for it. This one. Oops. This one over here. Well, this belongs to the y-axis, right? So on one hand, because it belongs to the y-axis, certainly the x-coordinate is 0. Correct? And now because it belongs to the graph of the function, any point that belongs to the graph of a function, the second coordinate must be the image of the first under the function. So the second coordinate must be f of 0, right? In this case, because I know that the first coordinate is 0. So the second must be f of that first, so it's f of 0. So algebraically, how do we find then the y-intercept? We just evaluate the function f at 0 and we give ourselves the y-intercept. So to find the y-intercept, we evaluate the function at 0. So that is to say, we find f of 0, right? So we only find f of 0 to fully determine the y-intercept. Back to that example. Over here, what was the y-intercept at the time? Let's do it again. It's f of 0, right? It's f of 0, and f of 0 is negative 2 times 0, so 0, plus 6. So 0 plus 6 is 6. It was this point, right? That's the y-intercept. So 6 is f of 0. We found it at the time. Okay. All right, let's take more problems from the book pertaining to this concept. This is on page 148. Let's do 84. Determine the x and y intercepts for the given function. 84. G of x is minus square root of x plus 3. So g of x, so 84, g of x is minus square root of x plus 4. Let me make sure I copied it right. Plus 3. So minus square root of x plus 3. Okay. Alright, so let's find the x-intercepts. And as we just discussed above, to find the x-intercepts, what do? We solve the equation f of x equals 0. The name of the function here is g, so I'm gonna solve the equation g of x equals 0. And this equation is equivalent to saying that minus square root of x plus 3 is equal to 0, which means that square root of x is equal to 3. Correct? If you add square root of x to both sides, that's what you get. Okay. So what's that x that does this job? X should be certainly bigger than or equal to 0. What's the x so that square root of that guy is 3? This means that the x is 9, right? So 9 is the only guy okay, so one more time. At 9, when the input is 9, that's the only time the function g is going to produce the output 0, because 9 is the only solution to this equation, g of x equals 0. So thus, the x-intercepts, actually the x-intercept, there's one and only one x-intercept here. So the x-intercept is 9, 0. How about the y-intercepts? The y-intercept, I should say. Well, I evaluate the function. Okay, the name is g here. I need to evaluate the function at 0. This is what we discussed right above, right? It's right there. So g of 0, that's minus square root of 0 plus 3, correct? So if you plug in 0, the 0 is going to sit here, minus square root of 0 plus 3. What's square root of 0? Square root of 0 is 0. The whole thing here is 0 plus 3 is 3. So the y-intercept then is simply 0, g of 0, which is 3. Okay. All right. Let me actually show you how the function is graphed. Let me go to this website, to Desmos, and graph the function. So the function was y equals minus square root of x, right, plus 3. You see how the function looks like? It looks like something like this. The y-intercept which we found was 0, 3, and the x-intercept is 9, 0. Correct? This is what we found. But what we found algebraically is way stronger than just looking at this picture or this graph, because who tells you that later the function doesn't curve back up and goes through the x-axis again? So which means how would you know if you just look at the small window here that the function doesn't cross the x-axis again. Even if you keep scrolling, you don't see it, but there's no guarantee because, I mean, this function keeps going to the right forever, correct? So there's no guarantee except if you solve it algebraically that there are no more x-intercepts. Okay, just wanted to give you a quick look at how the function actually looks like. Based on the discussion that we have, by the way, based on the discussion we had the algebraic discussion, we know that the function doesn't cross the x-axis again. Okay, all right, let's do one more. How about 80? So we want to find the x and y intercepts of the function q of x equals x squared minus 8. Okay, so this is 80. So we want to find the x and y intercept of the function q of x equals x squared minus 8. So let's find the x-intercepts. So how do we find the x-intercept? Again, we just we need to solve the equation f of x, or q of x in this case, equals 0. So we solve the equation q of x equals 0. The solutions are the first coordinates of the x-intercepts. This means that x squared minus 8 is equal to 0, right? Because q of x is x squared minus 8. And this means that x squared is equal to 8. Which means by the star property, remember the star property we discussed before in this video? This means that x is, let me just say star, so you know what I'm talking about. By the star property, x is the a in the star property and 8 is the b in the star property, right? This means that x is plus or minus square root of a. And square root of a, as you know, is 2 square root of 2. So x is plus or minus 2 square root of 2. Okay? So in this case, we have two solutions for this equation q of x equals 0, namely plus 2 square root of 2 and minus square root of 2. So this entails that the x-intercepts are two guys here, the minus 2 square root of 2 comma 0 and the plus 2 square root of 2 comma 0, right? Okay, how about the y-intercept? How about the y-intercept? The y-intercept, we have to evaluate the function at 0, and that would be the y-coordinate of the y-intercept. The first coordinate is 0. So q of 0 is simply 0 squared minus 8, right? Q of 0 is 0 squared minus 8, which is equal to negative 8. So the y-intercept is simply 0 comma negative 8, correct? So we have two x-intercept and one y-intercept, which is 0, negative 8. If you go to Desmos again, you look at the picture for x squared minus 8, that's the point which is 2 square root of 2 comma 0, okay, this one, and this point which is negative 2 square root of 2 comma 0. Square root of 2 is an irrational number, so it has infinitely many decimal points. This is an approximation. This is not accurate, obviously. This is an approximation of the negative 2 square root of 2. And this is the 0, negative 8, which is the y-intercept. Okay? So algebra is, the thing that we did on the page, on the other page, they are way stronger than what you just see here, because number one, it doesn't give you exactly the x coordinate of these 2 points. This is an approximation. 2 square root of 2 is not minus 2.828. It would be an approximation up to 3 digits after the decimal point, but it's not exactly negative 2 square root of 2. Neither this, right? This is not the exact number 2 square root of 2. All right, so yeah, these would be the intercepts. Let's now move on to back to the book and do one of these problems on page 150. Let's do 112. Okay, so let's copy this. Let's copy it and take it to here. Okay, so this is 112. So what is it? This was on page 150, number 112. So 150, number 112. Alright, so this is what we have. This is the function f, the blue pieces, right? So it blows up as x becomes large negative. Around 0, the function from the left it approaches 1, and at 0 it starts being at -4, right? All the way to 2. At 2 it makes a jump. It goes from -4 all the way to 2, and then it blows up as x increases. Okay. Alright, so let's see what the questions are. The first one, determine f of -2. So part A, we want to determine f of -2. Well, -2 is the input, right? F of -2 is the output if the input is -2. So I'm gonna go to the graph of f, because this is all what I know about f. I just know the graph of it. So I'm gonna go to the graph. I'm gonna go to the point, because any point on the graph of the function, remember, any point on the graph of the function has two values, a, f of a, right? So in this case, they want this a to be -2, right? So I'm gonna go to the point on the graph of the function whose first coordinate is -2. This is how I'm gonna determine f of -2. I'm gonna look at the second coordinate, and that second coordinate is gonna be f of that -2. Okay, so this is my strategy. One more time. Since any point on the graph of the function f has coordinates a, where a is in the domain, comma f of a, they want f of -2, so they want the a to be -2. So I'm gonna go to the point on the graph whose first coordinate is -2, and that's gonna tell me what the second coordinate is. Whatever it is, that's gonna be the desired entity. Okay? Alright, so let's go to the function, to the point of the function, or on the graph of the function whose first coordinate is -2. What is it? So where is the point on the graph of the function whose first coordinate is -2? This is -2, so I'm talking about this point then. Okay, so that's the point. That's the point whose first coordinate is -2, and second coordinate for sure is going to be f of -2. Why? Because this point belongs to the graph, and the second coordinate must be f of the first. That's exactly what we discussed here. Okay, and as such, what do you find for f of -2? F of -2, which is the y coordinate of this point. What's the y coordinate? It's 1, right? It's 1. So f of -2 is simply 1. Make sense? Alright, so let's erase this part and just write the answer. What's the answer? It's 1, right? Okay. Alright. Part B. Determine f of 3. Same game, but now instead of having instead of going to the first coordinate whose minus 2, now I'm gonna go to the first coordinate who's 3, right? So first coordinate who's 3, this is where first coordinate is 3. Where's the function? The function is right there. That's the point whose first coordinate is 3 and second coordinate is f of the first coordinate, which is f of 3. Okay? Alright. And now the question is, what is that y coordinate of this point? What's this height? Well, this height is 3. It's right there. It's the y coordinate of this point, which is 3. So too many 3's here. But the green 3 is the y coordinate. It's this one. And this 3, the purple one, is this guy here, right? Okay. So x comma f of x, a comma f of a, 3 comma f of 3, any point on the graph of the function f. So the first coordinate happens to be 3, the second coordinate is going to be f of 3, and f of 3 happens here to be also 3. Okay? Alright. So f of 3 is 3 then. Okay, part C. Part C. Find all the x for which f of x is equal to negative 1. So find all the x for which f of x is negative 1. Okay. So that's part C. Find all the x, all the real numbers x, such that f of x is equal to negative 1. Correct? This is the question. Let me check again. So I want to find all the x for which f of x is negative 1. Okay. So what does the question mean? The question mean, if we understand any of the first two, then we're going to understand all of them. Why? Because what am I after? I'm after all first coordinates whose second coordinate is negative 1. Right? This is the question. This is what the question means. So let me write it for you. So this question here means we want to find all first coordinates right of points on the graph of the function so that their second coordinates, so their second coordinate is negative 1, right? This is what the question is. I want to find all the inputs for which the outputs or the output is negative 1. Okay, so meaning for which points, for which input the function is gonna assign the output negative 1. So I'm gonna go to the function, right? I'm gonna go to the function. I'm gonna look for the y value being negative 1, correct? And for those points, I'm gonna just extract their x coordinates, because that's the question. They want the x coordinates. Well, if you take a look at the function, maybe I need to clean it a little bit. Let me just clean the graph. So if you look at the function, is there any point on the function whose second coordinate equal negative 1? Is there any point on the graph of the function whose y coordinate is negative 1? Well, for example, this guy, the y-coordinate is positive here, right? So certainly it's not -1. The y-coordinate of this point is also positive, so this is not what I'm looking for. How about this? When the input is -1, the output is 0, right? F of -1 is 0, so it's not -1 as an output. Any point on the graph here is the y-coordinate is positive, so none of these points have a second coordinate -1. As such, I'm not gonna take any of these first coordinates. The only piece that remains that still has a chance is this. Well, any y-coordinate here is -4, which is not -1, correct? So there is nowhere on the graph of the function a point whose second coordinate is -1. As such, there is no input so that the output is -1 through the function f. This function doesn't output -1, as you can see. What is -1 actually as an output? This is the level -1. That's the level -1. The question is, was there any location where this function is meeting that line -1, that height, that depth, -1? This is the question, right? Pictorially, this is what it means. Is there anywhere where the function f crosses this level -1? And it's clear that there is nowhere that this is happening, correct? Okay, so that is to say, I'm still writing the analysis here, so that is to say, is there, or find all locations, all x locations for which the function f intersects the line y equals -1, or the function y equals -1, this guy, right? This is the line y equals -1. And the question is there anywhere where this function and this line meet? Is there anywhere where this function f crosses that function -1? And the answer is they don't intersect. There's nowhere the two meet. There's nowhere that this matches this, right? So long story short, there is no x that do the job. Okay, so to answer the question, there is no x that verifies this equation, f of x equals -1. Make sense? All right, so the solution set of this equation, f of x equals -1, is empty. There are no solutions. Okay. Part D. Find all the x for which f of x is equal to -4. So part D, find all the real numbers x for which f of x is equal to -1 and -4 in this case, correct? So I mean, it's the same reasoning as before. So I mean, whichever explanation worked for you, let's employ it. So the question is there anywhere where the function f of x, where the function f and the line -4, because what's this function -4? It's a line. Do they, I mean, is there anywhere where they meet? If yes, give me all those inputs. Okay, so what is that line negative 4? What is that line negative 4? It's oops, let's see, it's this line, right? All right, with a grain of salt. I mean, all right, let me just erase it. Okay, so something like this. This is the line y equals negative 4, correct? It's a horizontal line. And the question is there any location on the real line, on the horizontal axis, for which this function f and the line y equals negative 4, the purple line, meet? Do you see anywhere on the graph where the blue graph and the horizontal line y equals negative 4 meet? Yeah, it's this piece here, right? This is where they meet, from here all the way to here. The question is, they want all the x that do this job, right? They want all the x locations that allow the function to meet negative 4, that allow this function to go that deep. Okay, well, so I want to see for which x coordinate, for which x locations this is happening. Well, this point corresponds to input 0, right? Right, the input here, I mean, the coordinates of this point are 0 and negative 4. So if you plug in 0, you get negative 4. So 0 solves this problem, right? F of 0 is negative 4. So 0 is a solution to this problem. So 0 is part of the, the numbers I'm after. Okay. Any number between 1 and 2 does the job too, right? Any number between 1 and 2 does the job. Why? Because if you take any number here, the function outputs negative 4 for this input, right? And now how about 2 itself? At 2, the function doesn't output negative 4 anymore. There's a hole here, right? It keeps outputting negative 4 as long as you get closer and closer to 2 from the left, but once you reach 2, the function makes a jump to height 2. So f of 2 is 2, is not negative 4 anymore, right? So 2 is not part of my solutions. It's not part of the solutions I'm after. But any point to the left of 2 and to the right of 0, this is 0 here, sorry, to the left of 2 and to the right of 0 is solving my problem. Okay. For example, this point here, it has coordinates 1 comma negative 4. So f of 1 is negative 4, right? F of 1 is negative 4. So if you replace x by 1, it's gonna be negative. The output is negative 4. So 1 is part of the solutions I'm after. And any number between 0 and 2, including 0 excluding 2, is a number that solves the problem. All right. So back to this. Find all the x for which this happens. Those x are given by, so any x that belongs to the set 0 comma 0 comma 2, including 0 out excluding 2, has the property f of x equals negative 4, right? Makes sense? All right, part E. Determine the x-intercepts, or the x-intercept. Well, let's clean the graph again. The x-intercepts. Is there anywhere where the function crosses the x-axis or intersects with the x-axis? The only this is the x-axis, right? this one. I should have not said crosses, I meant intersects. Is there anywhere where the function intersects the x-axis? Yeah, this point, right? And what are the coordinates of this point? Input, or first coordinate is -1, and the x coordinate, the y coordinate is 0. So part E, the x-intercept, there's one and only one in this case, is simply -1, 0. This is not an interval, this is a pair of values, okay? This is an interval. This is a point in the plane. Alright. Part F. Determine the y-intercept. Determine the point of intersection between the graph, the blue graph, and the y-axis. Okay. So where does the y-axis, this one, intersect with, you get the point, so okay, let me just shift it a little bit. Alright, so where does the function f, the blue graph, intersect the y-axis? Where the intersection happens here, right? At this point. This is the y-intercept. And what are the coordinates of this point? Certainly it's 0, f of 0, and f of 0 happens to be -4 in this context. Correct? So that's the y-intercept. So f, the y-intercept is 0, f of 0, which was -4 in this case. Okay, G. G, determine the domain of f. Determine the domain of f. Okay, so I need to find the domain. We know how to find the domain graphically now. We had a shortcut. We can flatten the function along the x-axis, or we can project all the points on the graph onto the x-axis, because I need to only retain the x coordinates of these points. This is what the domain is, right? It's the set of all acceptable inputs through the function. So if you project all the points of the graph onto the x-axis, right, this function is blowing up. It keeps going up like this. So you project all these orthogonally onto the x-axis. You're gonna start seeing all this piece, or all this part of the x-axis. All these points are coming from the projection of these guys, and then all the way to here at -1. If you project the point -1, 0, it means you are taking the input -1, and then you keep projecting, but here you have a hole, right? Here you have a hole. But don't forget, the function is also, this branch is also part of the function. Now if you project this point onto the x-axis, that hole is going to be complete now. It's not going to be a hole anymore. And you keep projecting all these points onto the x-axis, so you're going to complete those, right? So far, every point has an output. No matter where you are on the x-axis, you always you look up or down, you're going to see somewhere the function. At this point too, if you project this, it's going to project a hole, so I'm not going to see anything, but the hole is going to be filled with the point that comes from the projection of this point, and you're going to keep projecting. So at the end of the day, you're going to see all of this, right? Because this function keeps going this way. That's the understanding. So long story short, the domain is going to be everything. There is no input that doesn't have an output through this function, right? If you give me 4, the output is this guy, 4. If you give me 3, the output is 3. If you give me, I don't know, 0, the output is -4. If you give me -2 as an input, the output is 1, and so on and so forth. Okay, so bottom line, the domain is all real numbers, all the real numbers. So the domain is all of R. Okay, and the last part, part H, determine the range of the function f. This is part H. We want to find the range of the function f. Okay, so let's clean again. Alright, so the range. The range is the set of all possible outputs, right? Okay, so the function clearly doesn't produce outputs that are below -4, right? The function is nowhere to be found below this level, -4. Correct? The lowest output that this function produces is -4. I'm talking about the y values, right? The lowest y value that the function produces is -4. Okay? And now, does it produce anything between -4 and 0 while not reaching 0? No, the function is nowhere here, right? There's no output. There's no output here between -4 and 0, excluding 0. At 0, the function is gonna start producing this output, because if you plug in -1, you get the output 0, correct? And it's gonna produce all these values in between as an output, correct? For example, this point has this output, okay? And so on and so forth. Does the function produce the output 1? Yeah. This point has the y coordinate 1. So if you plug in -2, you get an output 1. So 1 is a possible output. So I'm gonna have also one part of the game, of the range, and all this branch, remember this keeps blowing up here, all this branch is gonna tell me that all these y values are gonna be reachable, right? Correct? I don't even need to look at this, because this guy, this branch here, completes this part of the y-axis. So all these values are reachable by the function. The function produces such outputs. Okay? So equivalently, we could have just projected all the points onto the y-axis, or flattened the function along the y-axis. Imagine you're squeezing, right? You're squeezing the function from both sides onto the y-axis. You're flattening it. What you see at the end of the day is this is gonna be squeezed. You're gonna be here. All these points are gonna be dropped onto the y-axis. You're gonna only see this part, right? Starting from 0. Correct? These points here, they're gonna be dropped, but we already accounted for these values. So long story short, -4 is part of the range, and any non-negative value is also part of the range. Okay? Alright, now we're gonna interpret this. Let's use interval notation to interpret this. How do you interpret this part? From 0 to infinity. I can say, okay, this is 0 plus infinity, like this. 0 closed, because 0 is a possible output. We discussed that. If you plug in -1, the output is 0, right? Because -1 comma 0 is part of the graph. Okay, so this piece of the y-axis is this, 0 plus infinity. But this is not all of the range. It's a significant part of it, but it's not all of it. We're missing -4, right? We're missing -4. So I'm gonna take this guy, I'm gonna join it, this is a set, I'm gonna join it to the set consisting of this guy, -4. How about this? Okay. So one more time, this part here is this branch, this part of the y-axis, but I'm missing -4. So I'm gonna join those values, I'm gonna join the set, take the union, to the set consisting of just -4. Okay, so let's copy that. So 0 plus infinity union -4. Okay, alright, so this completes this problem, and I'm gonna draw the line here for this video, but keep in mind I still have a small section, a small part. It should have been in the preliminary section, but I wanted to make the connection with the current section, so I'm gonna include it as an addendum to this section. Okay, so I'm gonna have an addendum to this video to include the part that should have been in the first video, in the first lecture video, but I saved it to make the connection with the current concepts. All right. Okay, so I'll draw the line here for this one.